Okay, so we'll start. Let them join. Induja, we can go. Sunil, just a minute. Sunil,
Yeah.
yeah, just unmute your video for just few minutes, then we can proceed. We can start almost 50 minutes of that.
Yeah, I'm trying that.
No, it's up to you. Yeah. Good morning, Sunil. How are you?
Good morning, good morning. I'm fine.
Yeah. Good. Yes, so Induja, we can start now.
A very good morning to one and all, and welcome to the third day of the online FDP on data analysis using econometric models, sponsored by ATEL and hosted by the Department of Economics, Central University of Tamil Nadu. I am delighted to welcome today's speaker, Dr. Sunil Paul Sir, Assistant Professor in the Department of Economics, School of Humanities and Social Sciences at the Indian Institute of Technology, Goa. He has worked as an assistant professor in the Madras School of Economics from 2014 to 2018. He has also worked as a visiting faculty in the Department of Economics, Central University of Tamil Nadu. He has a PhD in economics from Pondicherry University and an MA in economics from University of Calicut. Sir has published numerous papers in the fields of macroeconomics, monetary economics, and applied time series econometrics, including papers on monetary aggregates and core inflation evidence from India for the journal Applied Economics Letters, and Money and Inflation in India, evidence from P-Star model for the Bulletin of Economic Research. Now, I would like to invite Dr. Sunil Paul Sir to talk about today's session on multivariate time series models.
Good morning and welcome to all. Thank you, Dr. Balaji, for inviting me to the workshop. So today we will be covering vector autoregressions and structural vector autoregressions precisely. So we look what is the concepts, basic concepts behind vector autoregressions and identification problem in VAR. And let us start. I'll pause my video because I'm using my laptop as screen. I can use it for writing and all. Is it okay?
Yes, Sunil. It's for convenience.
So let me share my screen first. Just a minute. I hope my screen is visible, no?
Yes, man.
So I'll start with a little history, before going to the concepts. So Timbergen, he got Nobel Prize. He's one of the first Nobel laureates in economics. So he was one, and he was one who tried to use mathematical means, especially mathematical methods to analyze economic theories. And there is famous debate between him and Keynes. Nearly that debate is very famous on the use of mathematics and econometrics, and how Keynes argued it is not that useful in analyzing economic theory something. And later then, in order to address the Keynes criticisms, and Havelmo came in, he only gave probabilistic interpretation to this economic model that is developed by Timbergen. And later, following Havelmo, a lot of Keynesians built large system of equations running around hundreds of equations and that much variables for interpreting, forecasting, and conducting policy experiments. But these models were later criticized. Christopher Sims got Nobel Prize for his contribution to this field only. So he criticized on following accounts, because he said that Sims' observation was that most of these restrictions in identifying used to identify the relationship was incredible in nature, so it was not reliable anymore, because large number of system of equation and that many equations, that many variables, and putting restrictions on equations was arbitrary in nature. And selecting variables which is exogenous, which is endogenous, was devoid of any economic theory and statistical argument. So because of these reasons, Mr. Sims criticized the use of large macroeconomic systems. And he also said that these studies using these large equations were not only, it was not reproducible, and it's very difficult to compare with similar studies. Means similar studies that address same issue. So in this background only, Sims suggested, why can't we formulate unrestricted reduced form var? I'll explain what is this unrestricted reduced form var in a minute, where we treat all the variables as endogenous, and we try to express each variable as a function of its own past values and past values of other variables. Then we can use only few number of variables in this var system, and we can easily unearth the underlying dynamic relationship or interactions between these variables clearly, and we can use this model to summarize, formulate, and test economic theories in a structural model, or we can use it for forecasting and so on. So that is a very brief overview of the history of var modeling. This is how var modeling got into picture. So you might have already studied the AR model by now, I think. So AR model primarily means autoregressive model. A univariate autoregressive model, for example, primarily explains a variable as its own beta 0 plus beta 1 yt minus 1 plus beta k yt minus k plus epsilon t. So this is an AR model. So we can, I'll show in a minute, we can see var as a extension or a generalization of univariate AR model. And only difference is that we will have this vector, instead of yt as a variable, we'll have a vector of variables, and we'll express it as a function of its own and other variables, lag terms. And here, one of the speciality is that every variable, as I mentioned earlier, each and every variable used in exogenous are endogenous, so they are jointly modeled, and we can use this var model to forecast.
We are losing your connection, man. Dr. Sunil?
I think there's some connection issue.
Yeah, I understand. Let me call him.
Yes.
Please wait for 5 minutes. He will join. He has some network issues. Wait for 5 minutes. See, all of you are informed to switch off your mics. George, George, switch off your mic. Don't push me to mention my name. All of you make sure that you switch off your mic.
Oh, I'm sorry, I didn't realize was the network connection was gone.
No issue, doctor. Carry
Yeah,
on
I'll
now.
share it again. Where did I means?
No, when you talk about that return equation, that the red color.
Okay, okay. So I think I am audible. Hello. Hello. Balaji, can you hear me?
Yes, sir, we can hear you.
Trying to broadcast the screen. 1 minute. It takes time. Uh, so I was talking about this online. So I was talking about VAR as a generalization of AR model. So here each variable, like in autoregressive model also, you try to explain YT using the past values of YT. That's why it's autoregressive. So this is also a generalization. The word itself, vector autoregression. So only the difference is that instead of one variable, we use number of variables. And this following this, Stockton-Watson in his article in 2001 journal of, he published an article in Journal of Economic Perspective summarizing the means idea of autoregressions and literature that happened so far. And he describes the use, means he says that the following four not the listed one here. He said that the VAR can be used to describe and summarize macroeconomic time series, and we can use it to make causal forecasts, and we can also use it to recover to advise macroeconomic policy makers. So since the focus here would be on identification of causal relations, I am reformulating this as we are assuming that VAR will be useful to estimate the causal relationship. For example, how does monetary policy affect output or perform policy analysis? How should RBI adjust interest rate to get prescribed change in GDP or test economic theories? For example, you may be familiar with the real balance, the neo-Keynesian models, and so these theories, which theories, what theories you can trust, which theory is true or which theory is consistent with the data using VAR. And this is also used to get the D parameters for the DSG estimation. So to give a brief overview. So for example, if you consider a specific issue, you are actually considering a bivariate model. For example, with XT, with XT is equal to, say, two variables, real GDP and a policy rate. So you are interested to analyze or model these two variables, or run estimate a VAR with these two variables. So this VAR would help us to understand or help us to answer the following questions. So what is the dynamic behavior of these variables? So dynamic behavior of this variable and how they interact. And second, actually, it also will help us to understand what is the most likely path of GDP in few quarters, or what is the likely path of interest rate or rate variable in a few quarters or few months, whatever data you have taken, likely path of the variables, and what is the effect of, so rate variable is a policy variable. So what is the effect of monetary policy shock on GDP, effect of monetary policy on GDP, and finally, what is the historical contribution of monetary policy shocks to GDP fluctuation. So this kind of questions we would be able to answer using VAR. Am I online? Am I audible?
Yes, sir, you're
Yeah.
audible.
Yes, sir.
So consider a first order. So when we say about VAR, it has two basic properties. One is order, and other is actually length. So order says how many variables are there in the variable. So it is a no, order means how many lag terms we have included in the variable. So it's a we use only one lag of each variable. So order is one. So this is a first order bivariate. There are two length of this var is actually we use two variables. So length of this var is actually two variables. So this is a first order. This here I have written it as a system of equation. So we can write it in a matrix format, or we can in matrix format it will be say x t. It will come back to that again. Still I am writing it. So w say xt plus c1 xt minus 1. So this is plus epsilon t. So this is, we can write it in a matrix format where xt is actually the vector of variables, and b is actually vector matrix of coefficients, and so c1 is also vector of coefficients and so on. So this here actually we are writing it as a system of equation. So this is a bivariate first order vector autoregression, and this is also structural vector autoregression, because you see it includes same time values of xt, so yt as a function of st. So we have simultaneous relationship. It captures simultaneous relationship between yt and zt and zt and yt. So in both equation you can see the simultaneous values of zt and yt are included. So it's a structural var, and in addition to that, we assume you may be familiar with this notations. We assume yt and zt are I0, or in other words, these are stationary at levels. So and these errors are known as structural errors, epsilon yt and epsilon zt. So we are assuming that they follow a white noise process with zero mean and constant variant sigma square y square. And similarly, the both variables, both errors follows a white noise process with zero mean and constant covariance. And in addition to that, we assume that these errors are not serially correlated. These are the assumptions of structural var model. And in addition to that, we assume that yt, that already said, stationary means it has a constant variable, constant variance, and constant mean, and autocorrelation is also constant in lags. So if we change lag, autocorrelation change, but it is constant. And the coefficients b12 and b21 are actually it captures the contemporaneous effect of zt on y and yt on zt. So for example, if you take b12, it actually captures the contemporaneous effect of zt on yt, and this is the basic equation. When a simple var model will look like this, and as I said, in matrix form we can write it as so. This is actually coefficients of this is the coefficients of contemporaneous equation. Yt is a t, b1t, and this is the coefficient matrix with respect to yt minus 1 is a t. And you can easily get the equation that we have seen earlier by expanding. See, this can be, first equation can be written as beta 1 to sorry, yt plus beta 1 to zt is equal to b10 plus c11 yt minus 1 plus c12 zt minus zt minus 1 plus epsilon yt. So this is nothing but the first equation that we derived earlier. So it's not exactly the same because there should be a minus symbol here. So type. So to get similar right, similar equation that we derived earlier. This is the equation that we have here. Oh, here I used minus. So then it's this sign is correct. It's my mistake. It was minus b12. I didn't notice that. So this is the same equation that we put earlier. So this is the structural var in matrix form. So we can write it in many different ways, or we can also express in some papers. You may say that xt is equal to say a0 plus a1 xt minus 1 plus b inverse times epsilon t. This is also correct representation, where a0 is actually b inverse gamma 0 and a1 is actually b inverse gamma 1. Means we can write it, both are same. We can express this equation in many ways. So this is a structural var. As I said earlier, it actually it is a structural var because it captures the behavioral relationship, and this because we may be interested in the structural relationship rather than reduce from errors. I'll come back to this. What is the problem with this? These errors are also known as structural errors. So I'll come back to these structural errors and the meaning of why it is important later on, once we discuss the reduced form approximation or reduced form representation. So this is what same thing I have written here. So this I have already written. So B inverse, B is identity matrix. So this is A0, this is A1. B inverse epsilon T is the structural var. So this is a var in standard form. So here you see there is no simultaneous values of variables in xt in the left hand side or right hand side. So so this is a var in standard form, and you see this error et is the et here is equal to beta inverse epsilon t. So this is the reduced form errors, and we can actually estimate this var. The structural var we may not be able to estimate because of simultaneous bias, as same values appear in both equations. So we may not be able to identify the parameters of structural var, or we may not be able to estimate the coefficients of structural var in that form. but we can estimate the reduced form var using OLS or maximum likelihood or anything. So in other words, it doesn't have direct endogeneity. There is no problem of direct endogeneity in this reduced form. I am assuming that you know the assumption of simultaneous, means you know about simultaneous bias and what is the problem if there is simultaneous bias in estimating coefficient using OLS and so on. So reduced form var, in simple word, reduced form var can be, or parameters of this A10, A20, A11, all these can be estimated using OLS. On the other hand, the structural parameters are not, we cannot be estimated using ALS. So unlike this is actually reduced form error, and so we are taking, this is the variance covariance matrix of reduced form error, because this is very important. So in the variance covariance matrix of variance covariance matrix of say epsilon ZT, ZT YT. I think I'm using same covariance of epsilon ZT, epsilon YT, variance of epsilon YT. So this is the variance covariance of structural form. So this is equal to say sigma square epsilon y, epsilon is z, 0, 0, sigma square epsilon y. So you see the off diagonal values. So this variance covariance matrix of structural var is actually diagonal in nature, or because we assume that the correlation between these errors are 0. So unlike structural var covariance, the variance covariance matrix of var shocks are not diagonal, so they are correlated. So why they are correlated, we'll come back to later when I discuss the derivation and function in detail. So in var analysis, what is our strategy? So first you need to decide what are the variables you need to choose. That actually the theory would help you to identify that. And once you identify the variables, then you estimate the var by selecting the lab order P, by choosing the P using some statistical method. Then after estimating, you invert the var and get the impulse response of this var, or identify the impulse response, structural impulse response coefficients, and using that impulse response coefficient you can calculate, or you can understand the dynamic interaction between two variables. So that is how we do. So first as you choose the number of variables, theory may help you, or the problem that you are dealing with will guide you in choosing that. After that, var, while estimating the var, you need to decide what is the how many lags of these variables has to be included as explanatory variable, that you need to decide. That can be decided based on some theoretical model. Sometimes theoretically we need to include 2 lakhs or 3 lakhs. You can limit it like that, or you can use some statistical criteria to decide what is the length of, or what is the order of the var model. So basically order and length of var model can depend on your theoretical consideration also, but order can, we can use some statistical criteria based on Akaike information criteria, Shawson information criteria, or some other information criteria that is available in the literature, can be used to decide what is the optimum length of lag. So in order to decide that, see, we generally use Akaike information criteria or Shawson information criteria. So where the formula is given here, T is number of observation that we have of a particular variables, and sigma sigma determinant of sigma we use to, means it is actually similar to if it's a single equation variable, we'll be using residual square, so it's similar to that. So or we can use the log likelihood instead of residuals. We can use log likelihood, whatever it is. We can calculate the information AIC and Shawson information criteria using either residual square or log likelihood. So using this, if you are using any of this criteria, see, we take this is actually nothing but it's an approximation of residual square. So if residual square is smaller, then better the model. That is the criteria. Or if the log likelihood, the value of log likelihood is higher, then it is better the model. So according to that criteria, so what you do actually, you estimate a VAR with 1 lakh, 2 lakh, 3 lakh, or up to 10 lakh. And then you have 10 models at hand and calculate AIC for this model and AIC for VAR with 2 lakh values, AIC with a VAR model with 3 lakh values, 10 lakh values, and so on. And compare the AIC, compute the AIC and SBC following any of these methods. And once you compute the AIC and compare this AIC across these models, whichever model gives the smaller value for AIC or Shawson information criteria, that is better. And penalty in AIC for including more parameter is higher for the Shawson information criteria. So if there is any discrepancy in between these two measures, then Shawson information criteria will always tell us to choose the model with less lag values as possible. Once you do that, you can estimate the model using OLS or maximum likelihood, whatever you use. You can estimate the model. So first you choose the length of the VAR model. So you decide what all variables you need to include in a VAR model. It will be decided by your theory, means or the problem that you are dealing with. Economic theory will help you to identify the variables that can be used in this context. Then you decide the order of the R model. Order can be decided based on statistical criteria, as I discussed, AIC or Shawson information criteria, or you can use some theoretical. Theoretically, you have to limit the lag order to 2. That also can be used in some papers. They use like that. Then once you do that, you estimate the regression model. Can you, while estimating the regression model, how do you choose the best model? One or two key or one or two things that will help us to estimate a good VAR model is to check the residuals. So once you estimate the model, you check the residual. If residuals show some pattern, or if residuals are after including say 2 lakhs, if residuals show some serial correlation or residual show some pattern, then you can improve it by including more lag values. And you can check the model by checking the properties of residuals. Residuals should be white noise basically. So you can use Box-Jenkins Q statistics or any other LM test to understand the means understand whether you have used enough lag values in the model. Now, we will discuss some theoretical properties of VAR. This identification. I said this is similar to AR model. So you might have already discussed, you might have already learned about AR model by then. So AR model, if it is a simple variable, so you see yt is equal to say beta 0 plus beta 1 yt minus 1 plus epsilon t. If it is this is an AR1 model. So in this AR1 model, if beta coefficient, if beta coefficient is less than 1, then that AR model is stable. Modulus less than 1, then it is stable. If beta is equal to 1, then it's a unit root process or a random walk process. If it is greater than 1, then it's an explosive series. So similar to or analogous to this way of categorizing AR model, we can also discuss the stability and stationarity of VAR model using the properties of A matrix. Or in other words, we say if B1 is equal to 1, it's a non-stationary model. It's a random walk process. So similar to that, based on the values of or based on the properties of this A matrix, we can decide whether our estimated VAR model is stable or stationary. So, so to do what you do actually, if you are familiar with linear algebra, we can calculate the eigenvalues of A matrix. If it is A matrix is a 2 by 2 matrix, then it can have maximum 2 eigenvalues. So 2 eigenvalues. Based on this value of eigenvalue, we can decide whether the bar is stable or stationary. So you calculate the eigenvalues of A matrix, and if both the eigenvalues of matrix, if I assume that it's a bivariate VAR, that means we'll have only 2 variables. So then it's an 2 by 2 matrix. A is a 2 by 2 matrix. So if the eigenvalues of A matrix is less than 1, then we say that the VAR is a stable and stationary VAR. So if it is equal to, if one of the variables are equal, one of the eigenvalues is equal to 1, then it goes to this co-integration you might have come across. Provided both the values included in XT is I1 series and A matrix, only one of the eigenvalues is equal to 1 or less than 1, then it's a co-integrated system. If both values are greater than 1, then that VAR is not stable. And similar to AR model, see if an AR1 yt is equal to beta 0 plus, or for the time being I am doing this constant, but it doesn't change the discussion. Beta 1 plus epsilon t. We can actually invert it into an MA model. So just by taking assume that this time series starts at value y0, then for y1 it would be equal to beta 1 times y0 plus epsilon 1, and y2 will be beta 1 y1 plus epsilon 2, that is nothing but beta 1 times beta 1 y0 plus epsilon 1 plus epsilon 2, and this is equal to beta 1 square y0 plus beta 1 epsilon 1 plus epsilon 2. So we can invert, by recursively substituting these values backwards, we can actually derive the solve the value for yt, like something like this: beta 1 t plus 1 y0 plus, so this is initial condition, then beta 1 t epsilon t epsilon 1 beta t minus 1 epsilon 2 and epsilon t. So we can derive or we can actually invert this AR process into an moving average process by recursively substituting backwards. So this is a moving average representation of AR model. Similar to this, we can also derive a moving average. So we can write an ARP model like this. So AR1 is more easy to derive. So and here this AL is nothing but A0 plus A1 plus A2 means A1L, okay, L square plus A3L cube plus so on. So we can using lat notation we can write this ARP model as AL. L is the lag notation. XT is equal to A0 plus epsilon T. So once we have this, if we assume that all the eigenvalues are less than 0, means if we assume that the var is system stationary and stable, then inverse of this AL exists, and we can write this equation as AL inverse A0 time plus AL inverse epsilon T. So this AL inverse, if it is stationary and stable, or if all the eigenvalues of AL is less than 1, then we can similar to AR1, similar to the way we inverted AR model to MA process, VAR process also can be expressed as a vector moving average process. So this is a VMA, or we say that VMA representation of AR model. So where mu is nothing but AL inverse A0. This is the initial conditions, and this is the dynamic impact matrix. So dynamic impact matrix is like, if we expand this, you see we have consider a two variable var model, then it would look something like this: yt is a t is equal to mu y mu z plus say psi. Let us use the so let us see that coefficients of psi matrix is phi 1 1 phi 1 1 plus phi 2 1, say yt minus 1, not yt minus 1, et minus 1. E1t minus. First, I'll explain what it is. E1t minus 1, E1t minus 1 plus phi 1 2 E1t minus 2 plus so plus phi 1 2 E1t minus 2 plus phi let us use some other. Okay, 512 correctly. 5 instead of 5, let us say what variable, say psi, I'll use so say beta, say the beta 1 to e21 t minus 1 beta beta 1 t minus 1. So this plus say I'll write it here plus beta 1 e2 t minus 1 plus beta 1 2 e2 t minus 2, so on. And this one is similarly beta 2 1 e2 t minus 1 plus beta 2 t et minus e2 t minus 2. So this is a continuation of this thing. So this can be expanded like that. The meaning is actually this phi 1 2 and beta 1 2 beta 1 1 are the coefficients of phi matrix. So so this coefficient actually measures the impact of error term at time period t minus 1 on yt, and this measures the impact of error term on yt, impact of epsilon yt minus second period error term on yt, and so on. So these errors are the errors from the yt equation, and second e2t errors are the errors from the second equation. So it actually express yt as a function of lag values of error terms of e1t, that is first equation, and lag values of error terms of second error terms of
Excuse me, excuse me.
yeah.
I think your slides are not moving, man.
Oh, it's which
You are in slide number 19. Are you talking about that or what?
yeah, I'm writing. Can you see my writing?
No, man. It's on slide number 19.
Okay. Is it visible now?
Yeah, it's moving.
Yeah. Can you see this? So this
Yes,
is the
yes.
expansion
Yeah,
of
now we are able to see it.
yeah, this is the expansion of xyt. So xt is equal to phi 0 et psi 0 et, and these are the elements of this matrix. So the idea is actually we can express yt as a function of lag values of e1t and lag values of e2t. So this captures the dynamics or how these errors contributes to the evolution of yt and xt. That's what it shows. But this error term, this is actually impulse response coefficients. But these impulse response coefficients have some problem. So these elements of psi 0 are the impulse response coefficients. So psi 1.1 actually shows if there is a shock at time period t minus 1, what happens to yt, or if psi 1.1 shows what is the change in yt if something happens to error term of second equation, and it traces the changes in yt due to changes in the errors of first equation and second equation. So errors we can say in a time series equation yt, say if in without equation if we say that yt is a combination of e1 different errors, e1 plus e2 E2 plus E3 plus E4 plus ET. So this the value that we see at a particular time period is a accumulated error terms. So this in stationary we will have a coefficient that is less than in multiplied by, it's a weighted accumulated average, weighted accumulated impact of past values. So in the, if you take a GDP, some shock happens, say there is a deficit, rainfall is deficit in one of the years. So it's a shock. That shock will be captured by the error term. So if that, because of that shock, we get a particular value for error term at that particular period of time. So due to that, what change happens to this particular variable that we are dealing with, YT? That's what it measures. So this but has no economic meaning in a sense. Why it is? Because ET is a reduced form error. It is not a structural error. It can just it is just a forecast error. Nothing. It doesn't have any economic meaning. So why it doesn't have economic meaning is explained in this text, this slide. So ET is nothing but, see, ET is beta inverse epsilon t. So that means eta t, E1t is a function of both errors. See, E1t can be expressed as say if I say this matrix as say A1, let us say A10 epsilon yt plus A11 epsilon zt. So this is a function of these two errors. So whatever happens to, so this is the structural error of yt and this is the structural error of zt. So whatever happens in epsilon yt and epsilon zt will have some impact on E1t. So E1t is not a pure error, or it is a combined error of two variables. If you have it using bivariate VAR model, it is a combined error of yt and zt. So because of that, it doesn't have any economic reason. So we actually need to get impulse response that is given here. So impulse response with respect to epsilon yt and epsilon zt has to be identified. So this is the value you need to, or this is the coefficient that we need to recover. How do we recover these coefficients? What is the problem in recovering this coefficient? That's what our interest. So this is the expansion of this yt and zt. You see, yt, forget about this numbering, it's a typo. So yt, see here, it has expressed as a structural errors, present and past values of structural errors and present and past values of structural errors from zt. So we need to recover this 511.0.0, 511.1, 511.2 and so on, or 512.1, 512.2 and so on. These are the structural impulse coefficients. How do we recover that? So this 511.0 shows what happens to yt if there is a shock at time period t. So 511.1 captures what happens to yt if there is a shock at time period t minus 1 to y variable. Similarly, 5121 here captures the impact of shock in z variable on time period t minus 1 on yt, and what is the impact of shock in time period shock in zt at time period 2 on yt. That is what captured by 512.2. Similarly, for the z variables. So these are the this captures the, or this traces the impact effect of 1 unit change in the structural innovation. What happens if there is 1 unit change in epsilon yt on yt, or what happens if there is 1 unit change in epsilon yt minus 1 on yt, and so on. So this is what we are interested. So for a stable ARF, means stable var, if the eigenvalues of, so we expressed this A0 plus A1 xt minus 1 plus epsilon beta times inverse epsilon t. So we said that the var is stable if A1 is, the eigenvalues A1 is less than 1. So if A1 eigenvalues of A1 is less than 1, then this IRF that we calculated, this IRF will converge to 0. Why? Because if a variable is stable and stationary, then if some shock happens in the immediate past, it will have more impact than something that happened 5 years back or 10 years back. So if there is some deficit monsoon 5 years back, it will have less impact on today's GDP than previous year's deficit monsoon. If previous year we got less rainfall, then it will have more impact on GDP at current period than what happened 10 years back. 10 years, what happened 10 years back may not have any impact as of now. So it will converge to 0 if it is stationary and stable. If the eigenvalues are, so impact will be, or the values, these subsequent values of 5, 1, 2, as we take the lag values, as we go back to the time, impact will be less and less. So that is what it says. It will converge to 0. So 10 years back, if something happened, there is a supply shock, it may not, sometimes it may not have any impact on GDP at current period. If something happened in the previous year, that will have more impact. So the corona shock that happened in 2020-21 will have an impact on current period's GDP. But after 10 years, it may not have that much impact. That is the idea. So if we take the sum of all these coefficients, then we take, so if you want to know after 5 years, what is the impact of this corona shock? So in order to understand that, then you take the sum, if you estimate a var with this variable and GDP, and you take a sum of these coefficients, then you will get the cumulated impact of this shock, long run impact. So, so our interest is in understanding this structural impulse response function. But reduced form was, we may not be able to identify that. But we can estimate only the reduced form errors. So how do we recover these structural shocks from reduced form var? That is what identification means. So if we take the var, consider var in primitive form. See, this is the standard var. Xt is equal to a0 plus a1 xt minus 1 plus et. And the structural var formation of this is actually beta xt is equal to c0 plus c1 xt minus 1 plus epsilon t. So what is the, we can estimate this one, first one, but we may not be able to estimate the second one. The problem with, if it is a bivariate var, the problem is actually here, you see how many unknowns are there. Here we have 2 coefficients, here we have 4 coefficients, and here we need to estimate 3 coefficients, 3. So 2 plus 4 plus 3, 9 unknowns are there. But in a structural var, we have 2 unknowns here, 2 unknowns here, and 4 unknowns here, and 2 unknowns here. That means 2 plus 2 plus 2, 4 plus 2 is actually, we have 10 unknowns and 9 coefficients in reduced form. So reduced form in that to bivariate first order VAR, we have 9 parameters that can be estimated, and in a structural VAR we have 10 parameters. The question is actually how to recover these 10 unknowns. So these 9 parameters will be known once we estimate the reduced form VAR. So how to recover these 10 unknowns, whether we can recover these 10 unknowns using 9 estimated values of reduced form parameter. That is the question of identification. It is not possible. No, we cannot. We have 9 equations and 10 unknowns. It's not possible to recover all 10 unknowns. So to recover recover the unknown parameters of structural VAR, then we need to restrict one value of the structural VAR. We should have 9 equations and 9 unknowns. How to do that? That is the problem of identification. How to recover the unknown structural parameters from estimated reduced form parameters. So this I'll explain later. See, this is the structural VAR. B1 B matrix YT. This is nothing but B by T plus B0 plus C1 YT minus XT minus 1 plus epsilon T. This is the expression for this. Now we can take this is nothing. This can be written as B xt is equal to say A0 plus A1 xt minus 1 plus B inverse epsilon T. So this is the B inverse. So this B inverse can be recovered by restricting B21. So we are restricting B21.
Sunil, Dr. Sunil, just a minute. I think better you can share your screen again. Participants have some issues. Just share your screen again, then.
Yeah, my writing is also visible, no? Or
yeah, it's visible. It's a problem for everyone or only for few people? Because even I am able to see the screen properly.
Screen visible.
Clearly. It was visible clearly. Now it is not there.
No, he's just now close. I think those people who are using mobile, they face an issue because my thing is very clear here.
No, on mobile also it is very clear.
No, ma'am, I think some persons have some issues. They keep on posting. I request the resource person to share the screen again. Yes, Sunil, I think you are fine, man. You carry on. It's the problem with them actually.
Yeah. Can you see
Thank
my
you.
screen now?
Sorry.
Can you see
Yeah,
my
it's clear,
screen
man. It's
now?
clear, please.
So the idea is actually by restricting one coefficient. So I'll explain the reason, means the mathematics behind this later on. So by restricting this coefficient, we can recover the even. So by restricting one, so recursive or we restricted, then we are able to recover the complete second equation is completely recovered because B20 can be equated. So this is the reduced form YT. So we can see parallels. This B20 can be recovered from A20. A20 is we can estimate, and C21 can be recovered from this is equal to A21, and C22 is equal to A22, and this error will be equal to the structural error of ZT. So we can recover one structural equation by restricting one parameters in the B matrix. I just restricted one parameters in the B matrix. So we can recover that matrix. Once you recover the structural parameters of B20 and C21. So by plugging these values into models, so I have explained it next. This is the complete record. See, A11 is recovered. So A1 is estimatable, and we'll get value for we have restricted B2 B12, so we can recover. It's easy to explain from here, I think. So I'll use this itself. So here is actually, you see, A11 A10 is equal to B10 minus B12 times B20. So once you recover so once you recover B20 by plugging these values of B20, we can easily, and A21 you have the estimated value for A10, and you have recovered this value. So plugging this value, we can easily get value for B10, and similarly we can get B21, 12, and all other structural, or C11, C121, and C22. All these structural parameters can be recovered from B12 also can be recovered using this, because by restricting one value we can get all the values of structural parameters. That's what I've given here, because this is recovered from restricting, and once we restrict we can get the value for B12. Once you get the value for B12, we have the value for epsilon ZT. Using epsilon ZT we can recover the variance error terms of epsilon YT. Similar for every other variable, all the structural parameters can be recovered just putting one restriction. The problem was actually we had 10 unknowns and 9, so we estimate 9 parameters from reduced form form. That is means that we have 9 equations, because all these 10 parameters can be expressed as a function of reduced form parameter. So this is 9 equations. So by restricting one value here, we'll have 9 unknowns and 9 equations. So it's easy to recover these 9 unknowns once we restrict. That's what it's done here. I have a numerical example. You see, this is a reduced form R. So we can estimate, we will get the values of this one, and we can also estimate the variance covariance matrix once you have the, so all these 07, 02, 0 means all these numerical values can be estimated using OLS. So now we need to, using this VAR model, we need to recover the parameters V12, V1, C11, V21, and sigma epsilon y, sigma epsilon z. All these values has to be recovered using the estimated values of reduced form R. This we can estimate. So then, so this is how here what we do, we will restrict one value, that is beta21 is equal to 0. By restricting this value, we can easily get the equation, the epsilon sigma epsilon y is equal to 0.4 plus 0.5. By just solving this equation, we will get the expression for epsilon sigma epsilon y, and sigma epsilon z is nothing but, once we restrict, we can easily recover, that is nothing but 0.05. So solving this, now we have an equation solving this, because sigma, solving this equation, we will get the value for beta12. It's very easy to solve this equation. So once you have this beta12, then all other, so A11, A22 is recovered because we restrict B21. A21 is recovered because we restrict B21. And once you get these values by plugging these values into this equation, we'll get C11, we'll get C12. All the coefficients is recovered, and this is the structural VAR, because it is expressed in as a function of structural errors. See, by restricting the B12 is equal to 1, we are actually assuming ZT is affected only by ZT sigma epsilon ZT simultaneously. But you see the Y equation here, both errors are appear as explanatory variable, epsilon YT and epsilon ZT. So using this, we can get the impulse response. So you can actually sorry. You can actually write this VAR model, structural VAR model, as MA vector moving average process. So once you write it as a vector moving average process, then you would be able to recover the impulse response coefficient. This is what I have done here at time period t. So it's easy to check the. So I'll use this. If there is say 1 unit increase in means if there is a shock to y variable at time period t, what happens to y? Y will increase by 1 unit. And if there is a shock, 1 unit shock to zt at time period t, what happens to yt? Yt will increase by 8.8 times. Similarly, if there is 1 unit shock to zt, zt also will increase by 1 unit. That's what I have written it again here. So 1 unit shock to z, gem 1 unit means gem z by 1 unit and y by 0.8 units, and we keep all other shocks as 0. So we can, by doing this exercise, we can also get what happens to zt at time period t plus 1. That's what I have done here. So what happens? We know what happens to zt and yt if there is 1 unit shock. So in the next period, what happens? It is 2 times yt. So it is 2 times 0.8 because yt is 0.8. If there is a unit shock in zt at time period t, yt will increase by 0.8 units. That's why it's 0.8 units. And zt will increase by 1 unit. So by solving this, we'll get zt plus 1 next period. Zt will be equal to 0.8. If there is 1 unit shock in zt, at next period, zt plus 1 will be equal to 0.8 and yt plus 1 is equal to 0.76. Similarly, we can recover all the values. So this is what I have done here. So at time period 0, yt increases by 0.8 if there is a shock to z variable. Okay, zt increases by 1 variable. At next period, yt plus 1 will increase by 0.76 and zt plus will increase by 0.86. In time period, one more, if I update one more period at point t plus 2, yt will increase by 7.7 and zt will increase by 0.75. So like that, we can recover what happens to, or we can recover the path of yt and we can recover the path of zt. What happens to yt? There is a shock to zt variable for the next period and next period and so on. And what happens to yt if there is a shock to zt? So we can recover this impulse response. So the complete picture of impulse response is given there. If there is 1 unit shock, what happens to each variables at each period? And what if there is one? This table summarizes what happens to both variables if there is 1 unit shock. I have only given for 2 periods. We can update. It's just a numerical manipulation. It is nothing more than that. And for the yt also, if there is 1 unit shock in yt, what happens to these 2 variables? So yt will change by these numbers. At one first period, yt will be is equal to 1, zt will be is equal to 0. In the second period, zt will be 0.7, and so on. So we can get or we can identify what happens to these two variables when there is a problem, when there is a shock. So in general, how it is identified, I have explained it earlier. I'll go through it. So it's very easy. It's a simple mathematics. So we use this mathematical these things. So we have we have to see variance covariance matrix of reduced form R is actually sigma square 1, sigma 1 2, sigma 1 2, sigma 2 square. So these two are variables. So it's a symmetric matrix. So Cholesky decomposition says that this symmetric matrix can be decomposed into a lower triangle, that is actually say A11, A22, A21, 0. And it is transpose 0, A11, A22, A21. So this using this mathematical equation or mathematical fact only we achieve this decomposition. So the restriction of beta 0 is ultimately similar to decomposing the variance. Actually, we recover by decomposing that Cholesky means variance error. This we have done. So you can check the stability and all these things by checking the eigenvalues of A matrix. So this I already explained, but we used a second order VAR model. So if we in general we can actually extend this by to n order or n VAR with n lag. So if a VAR has n parameters, then we may have to restrict these many parameter n square. So if it is 2, see 2 is 2, 4 minus 2 divided by 2. So we have to restrict one parameter. So if it is a if your var has 3 variables, it is actually 9 minus 3 divided by 2. That is two parameters has to be restricted, and so on. So if it is 4, so n square minus n divided by 2 parameters has to be restricted to get the structural parameters. Now, so this is what impulse response. I hope you understood. Impulse response will help us to understand what happens to a variable if there is a shock. The variable or its own variable, and we can actually track the path of that variable. So another important results from VAR is actually variance decomposition. So this is the variance vector moving average representation. Here we represent yt and zt as a function of its own error, structural errors, and structural errors of zt for both variables. Now, so let us use the matrix notation here. We can update this PMA representation. See, we are updating zt by 1 period. So zt by 1 period by updating will get zt plus 1 is equal to x bar and phi 0 t plus 1. You see the representation here. it is yt, so this will become t plus 1. So epsilon t plus 1, epsilon t is a function of epsilon t plus 1, epsilon t plus t, t minus 1, so on. You can express, it's a vector moving average representation. So xt is a vector of variable yt and zt. Now, what is the expectation of xt plus 1 at time period t? At time period t, we know the value of epsilon t plus 1. So this is what is the expectation of epsilon t, that is equal to 0. So if the epsilon t's are known at time period t, or epsilon t plus 1 is known at t period time period t plus 1, or at period t of t plus 1 errors, then this would be equal to 0. So expectation of xt plus 1 then would be equal to x plus then this term. That's what written here. Now this is the conditional expectation. So this is nothing but conditional expectation of xt given xt plus 1, or given more generally xt given information as expectation of, sorry, it's not that. It's actually expectation of xt plus 1 given given the information at time period t. So that is nothing but forecasted value of xt at time period ft, time period. It is nothing but forecasted value of xt at time period. So let us say this is the forecasted value of xt at time period t plus 1. So if in that case, if I take the difference between xt, this is the actual value and this is the forecasted value of xt plus 1 at time period using the information at time period 1, then difference between xt plus 1 and forecasted value of xt plus 1 is nothing but this term. This is the forecast error that we are making if we are forecasting xt at time for the time period t plus 1. So this is one period ahead forecast error of xt. So similarly, if you update xt to xt plus 2, if you update it for xt plus 2, what you get? So you will get xt plus 2 is equal to x bar plus 50 epsilon t plus 2 plus phi 1 epsilon t minus t plus 1 plus phi 2 epsilon t and so on. So this term will become the forecast error for the next period. So by taking just difference between xt plus 2 and its forecasted value at time period t for t plus 2 is nothing but this one. So this is the forecast error for time period t. So similarly, for time period t plus n, then the forecast error can be derived like this: phi 0 epsilon t plus n plus phi 1 epsilon t plus n minus 1, so on. Now, in general, this is in matrix format now. So if you take separate these equations separately, then we can find that the forecast error can be, so if I this is the forecast error. If I take expectation of this forecast error yt plus 1 n, or if I take expectation to xt plus n minus expectation of xt plus n square, then you will get variance, or variance of xt plus n, or that is equal to sigma square y n. That's what we have here. So if I take this square, then this will become sigma square t plus n, sigma square sigma square YT n minus 1, so on. And 511 and 511.1, 511.1 512.0, 512.1, all these things are constant. So I can take constant outside, and this term, it can be written as like this, or in other words, it can be decomposed. The variance forecast error of YT and ZT can be decomposed into forecast into variance due to its own shock, this term, and variance due to other variable shock. For the in the case of YT, this one and this one. For the case of ZT, this term and this term. So we can easily understand how much uh, how much of the forecast error variance is explained by its own shock and the shock of other variable. So so if in this case we can identify what causes or what is an important, means whether another if we have two variables ZT and YT, whether other variable is important in explaining ZT, that can be understood by this various decomposition. So if ZT can explain none of the forecast variance of the other variable YT, then we can consider YT as exogenous. Similarly, if ZT can explain most of the forecast error of YT, then YT is an important variable in explaining ZT. That kind of inferences we can make. We follow the same identification for identifying these variance decomposition. So together with impulse response and variance decomposition, we call it as innovation accounting. Now let me so final touch, let me take one example. Not able to, won't be able to do the hands-on, so this is a paper by Killian, some co-authors, on oil shocks. So you know, oil shocks have an important role, or it is considered to be an important variable in the macroeconomy. So in the sense, many recessions have preceded by the increase of oil price. So to understand why it happened, so there are many studies who looked into this aspect. What are the effect of an oil price shock? If there is an increase in oil price, crude oil price, what happens to the GDP, or what happens to inflation and all these things? So in this paper, Killian actually tried to answer what kind of oil shocks are there and how these different kinds of oil shock affect GDP. So in order to do that, he used a war model to distinguish between different oil shocks. So this was his model. He followed an identification matrix that is equal to A0. His lower triangle, upper triangle was restricted to 0 because it is a 3 by 3 or it's a 3 variable var. That means we need to restrict 3 coefficients to recover the structural parameter. So that 3 coefficients restrictions is given here. So the identifying restriction, in other words, was this. He used 3 variables. One is actually growth rate of oil production, and a variable that proxies real global economic activities, and a variable that captures the real price of oil. These are 3 variables he used. And the vector, this is the vector of ZT. So based on this order and these restrictions, we can say that the identifying assumptions of his paper was this: oil production does not respond within a month to oil demand and oil prices. That is what this 0 signifies, both 0. So this is oil demand. First variable is oil demand. So oil production does not respond to 1 month's oil demand and oil prices. These two variables are zero. World demand is affected by within a month by oil production, but not by oil prices. So this is the world demand. Second variable is the world demand. So it is affected simultaneously by oil prices, but not by oil prices, but not by oil prices. Oil, it is affected by oil production, but not by oil. Oh, not this one. It is affected by oil production. This variable. This is not. This is unrestricted, but not by the oil prices. And oil prices, the third equation, third line. Oil prices responds immediately to oil production. This one D, and oil world demand, and this is the coefficient with respect. So it's not shown. So this D and E is significant for the oil prices. That's what 3D goes. These were the three identification or identifying assumptions by which he recovered this oil shocks, or he recovered these structural shocks. So this is what I have explained now. So production is not simultaneously influenced by either oil prices or world production. The real production is affected by the oil production, but not by oil price. Oil price is affected by both these two variables. So the oil production reduced shock is, so these are the structural shocks. So epsilon T is the oil production's structural shocks, and this is structural shocks of real activity, and this is the structural shocks of real oil price shocks. So this is how he identified. So so there are other identification methods. This is what I explained earlier. This variance decomposition of structural error, and this is the variance covariance of reduced form error. So from reduced form error can be written as this. So, or in other words, reduced form error, that is ZT, can be written as, so this is a diagonal matrix, say D and C transpose. We can decompose. This is following Cholesky decomposition. So this is the structural error. This is the reduced form error. So we can decompose this in this form. These coefficients of C then is the coefficient of V matrix. So this is one way of recovering structural errors. So there are different identification schemes. I'll discuss one more identification scheme. So we can follow. See, if you theoretically, so this uses Cholesky decomposition. This is this is this statistical, just application of a statistical or mathematical concept. But we can recover. So if it is a 2 by 2 matrix, only thing is that we have 10 unknowns and 9 equations. We need to restrict any one of the coefficients. So you can theoretically impose these restrictions on these variables. So if you have a 3 by 3 VAR model, so I can have a restriction scheme where I allow for this one, and these two are restricted, and this is restricted, A31 and A32. So I can follow a restriction scheme. I can theoretically impose zero restrictions on these coefficients of this A matrix differently also. So I discussed a symbol identification scheme in structural model. Only thing is that out of 10 parameters, if it is 2 by 2 matrix, or if it's a three length, three order var, or a var with 3 variables, then out of 18 variables, any of the out of it in this contemporaneous coefficient matrix, any 3 coefficient has to be restricted. That is the only concern. We can recover by restricting any of these parameters in the contemporaneous impact or coefficient matrix. So extending this Cholesky decomposition, using Cholesky decomposition, I can discuss one more identification, and with that I'll stop the discussion. So the identification that we discussed so far were concerned only with the B matrix. So B matrix, this is actually short run restriction. We are restricting any coefficients in these B matrix is short run restriction. So there is another, because it actually these coefficients in this matrix, B matrix, is actually short run coefficients that captures the impact of contemporaneous relationship. But I can, if I am interested in long run restriction, then we need to follow a different identification methodology. So for that, actually, we assume the variables to be stationary in first difference, or in other words, the variables yt is assumed to be I1. Any of these variables, either xt or yt, should be I1. So that's why we are taking change of yt and change of yt, assuming yt and zt are I1. So then zt delta yt will be an I0 variable, and delta xt is also will be an I0 variable. So we assume the variables in level as I1 variables, and its first difference as I0 variable. Now, how to means now we will be restricting the long run impact. So if there is a long run, suppose yt as GDP and is xt as some money supply. So now we need to recover the structural parameters by assuming that in the long run, aggregate the permanent shock of money supply on GDP is 0. That's the restriction we wanted to impose. To do that restriction, we need to follow this Blanchard and Coase restriction methods. So this is the model, reduced form model, and we can easily, yeah, yes.
Sir, are you presenting, sir, slide number 5?
No, it is actually 59.
Sir, the presentation is showing slide number 5, I think, and that is why we cannot connect.
Mr. Sean, because I'm also able to see slide number 15. Just got refreshed. Okay. There may be
Okay,
problem
sir.
from your side. My side is very clear. It's got recorded also. Anybody has any problem?
No,
The
sir. No,
presenters is in slide number 7. Yeah, we are able to see. Maybe problem with your side, please.
Yeah. So this is the reduced form one. No, we can write it as a VMA format that we already discussed. So we can write it in VMA format, and the sum of this is the parameters of this. Once we write into VMA format, the long run level effect can be recovered by the D matrix. That is I times B plus B square plus B3 and so on. So this is nothing but this can be written as if B matrix is a stable and stationary matrix. Then we can take the inverse of or we can write this expansion like this, and we assume there exists an inverse. So we can write it as identity matrix minus B all inverse is equal to 1 plus B square, assuming that the eigenvalues of B matrix are less than 1. So then this we are substituting 1 plus B square B3 with 1 minus identity matrix minus B inverse times C. This is the long run impact. So this restricting the coefficients of this D, then we can recover the coefficients, now recover the structural coefficients. So D transpose in that sense will be equal to 1 minus identity matrix minus B inverse C, and it is transpose. So so then if I restrict, so this is equal to this matrix, and C transpose is nothing but the variance matrix of reduced shock. So this is an it's symmetric matrix, so it can be decomposed using Cholesky matrix as C transpose. So using this results, then if we restrict the coefficients of one of the D matrix, so we are in short run matrix, we are just taking Cholesky decomposition of ZT directly. So Cholesky decomposition, this in short run matrix, we are taking the Cholesky decomposition of sigma directly. But here what we do, we take the Cholesky decomposition of this this term or D matrix. We multiply the variance covariance matrix of reduce. This is the variance covariance matrix of reduce from R. We multiply this with long run impact coefficients. This is the long run impact coefficient, and it transpose. We multiply it, and then you take the Cholesky decomposition. So first you estimate a model. So you will estimate in this case you will estimate beta 0 plus beta 1, or I'll use the same. So you will estimate this model ZT is equal to beta ZT minus 1 plus C epsilon T. So once you estimate this model, you can take inverse, take the identity matrix and take the difference of one, or take this identity matrix minus B. B is estimatable. This is estimated in reduced form R. This coefficients also can be achieved by estimate reduced form R. So once you take the inverse of this entity and multiply it with reduced form R, reduced error covariance matrix. This is also all these parameters of coefficients of B matrix, coefficients in the sigma matrix can be estimated using reduced form R. Once you estimate that, you get the matrix something like this: identity matrix minus B inverse epsilon sigma and its transpose. So once you get this value, this matrix, so this will be a 2 by 2 matrix if it is a bivariate model, say C11 or D11, D12. No, let us use some other word. Let us use P11, P12, P21, P22, and this two P12 and P21 will be equal, because because of this sigma matrix characteristics. So once you get this matrix, is a symmetric matrix, we can apply the Cholesky decomposition on this matrix instead of applying Cholesky decomposition on sigma matrix directly. You multiply sigma matrix by long run coefficients, that is identity matrix minus B inverse, and once you multiply that, you will get a matrix something like this, and you then check the Cholesky of this matrix. P11, P12, P21. So once you get the Cholesky of this matrix, then this, suppose this is the P matrix, this can be written as D transpose D. No, D, sorry, D, 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 D transpose. So this P matrix is this one, and this P matrix can be decomposed into D transpose using Cholesky decomposition. Once you do that, then you achieve the you can recover the structural parameters using structural means long run restrictions. So this is what I have done here. So I used P while discussing. I used P. What I meant was no, correct only. This is another way. So in Balajan and Co, I would have shown the hands-on if it was offline, but you can go through this article written by Blazer and Co. It is clearly, it's an easy to read article. So they used a two variable. They estimated two variable VAR. So they have used GDP and unemployment rate. So GDP is I1 series. So they have taken the first difference of GDP and unemployment rate. So either of one of these variables, either if you are using long run restriction, at least one of the variables should be I1. Then only there is a long run impact, or then only there will be a long run impact. So in this method, they were trying to understand the means they try to understand the importance of supply shocks and demand shocks using this model in the long run. So it's an important discussion in macroeconomics. You know, Keynesians emphasize the importance of demand shock but classical economists actually real business cycle approach. You know, they say their supply shocks are important. So in order to identify or in order to see which theory is correct, they use this long run restrictions, and their results shows that demand shocks were responsible for vast majority of short run fluctuations. So they could decompose this long run and short run impact using these long run restrictions. So to summarize our discussion, I know it was very means we did cover a lot of things in a very short time. So ultimately, VAR actually help us to summarize the information contained in variables. As we saw that how we can recover this information using impulse response as well as various decomposition. And VAR model, we can use VAR model to conduct experiments, or we can use VAR model to understand the dynamic causal relation between two or more variables. And it is done through identifying the structural VAR model using the estimated reduced form model, because we cannot estimate the structural VAR model because of simultaneity bias issues. So we have to estimate the reduced form VAR, and once you get the reduced form VAR, we can easily recover this impulse response and understand what is this causal relationship. So this VAR model is in that sense very simple. It's just statistical model. Once you, we need not in a symbol means if you want to understand a benchmark model, you can estimate this model without any theory. Once you estimate this model, then you can do this economic interpretation by appropriately restricting the coefficients of B matrix, and you can recover the structural parameters. Then you can give economic interpretation. So while estimating, you need not worry about theory, unlike previous large macroeconomic models. So it requires very minimum set of restrictions. So if you use Cholesky decomposition, we require very minimum. It's just a restriction based on mathematical theory. So once you get the results, you apply the theory later on. So with this, I will stop discussion on VAR. I hope you understood the idea behind, or how to read a VAR model, what is the idea behind VAR model, how it can be used. I hope you understood these things. Thank you.
Thank you, Dr. Sunil. So the participants have any questions, please post it in the chat box. Any questions from the participant side? Okay, actually, one of the participants is asking a question that whether is there is any condition based on which we restrict the value in the matrix. That is, based on economic theory, if you want to restrict anything in the matrix.
See, there are different ways to restrict. We explained only two identification schemes. That was basically based on Cholesky. But see, you can assume, you can put sign restriction. You can assume that in beta matrix, some of the values are negative, or it should be positive. So that kind of restriction you can keep. You can keep zero restrictions as we did now. You can keep any restriction based on theory. Your theory should give indications for that. If theories say that one variable is not contemporaneously related to other variable, then that's a zero restriction. If theory says that one variable is negatively related, contemporaneously related to other variable, then you can put signed restrictions. So I haven't discussed those identification scheme here. We have only used Cholesky based two identification theory schemes. So Cholesky is very simple because only lower triangle and upper triangle values are either at upper triangle or lower triangle is restricted, so it can be easily recovered. That's why I use that. But you can theoretically you can keep any, and theoretically you can restrict any values of B matrix. So we have a B matrix like this. Suppose B11, B12, B21, and B22. You can restrict any of these values to zero in general. We didn't do that because it requires more time to discuss. Or we can restrict some of these values. We can restrict beta 11 and beta 22 is equal to 0, or beta 11 and beta 21 is equal. So we can put any restrictions, or we can keep sign restriction. It should be minus. This should be minus. So that is decided by your theory. Theory should give your judgment should be based on your theory.
So actually one more question. Actually, that is not known to this. Someone is asking, how can we decide the lag length while using AAC for doing Granger conformity test? So AAC, see what we do, we run. Suppose you have estimate a VAR. So we estimate with say 1 lakh, 2 lakh, 3 lakh. So you decide maximum lakh up to 10. So you estimate VAR with 2 lakh, 3 lakh, 4 lakh. System will estimate if you are using a software package. Up to 10 lakh, you will have 10 models. So VAR with 1 lakh to VAR with 10 lakh. So using all these VARs,
using, yeah, hello.
Yes, man, you carry on.
Using these var, for each var we'll get either residual square, or we can calculate the maximum log. So using that maximum log, you will get AIC value for each of these values, each of this var. So for same variables. So AIC values for all these var models you will get. Then you compare the AIC values for this. You have 10 AIC values now. For var with 1 lakh, you will have one AIC value. For var with 2 lakh, you will have another AIC value. So you compare these AIC values and choose the lowest, choose the model that with the lowest AIC value. So the lowest AIC value actually optimizes the lag length.
Okay, there is one more question regarding which method of estimating lag is best.
Means?
No, the
AIC
question
or
is AIC or SBC or
yeah, the difference. See, that's
HQ.
yeah, that's all. Your judgments. You have to see how your residuals behave and all these things. Generally, Shawson information criteria penalizes inclusion of or penalizes over parameterization. You see the equation we have seen. No, the equation penalizes. There is an additional term.
Yes, maybe the last question because already sir was joined.
Okay, Shawson information criteria penalizes inclusion of more parameters. So it will always choose a model with less parameters if you use only statistical criteria. But your decision should be based on behavior of you. Once you estimate, you can see how your residuals behave, whether they are right or some theoretical. If you have some theoretical consideration, that also can be considered. Yeah.
So one more final question. The question is, I could not get the statement. The impulse response due to shocks has no economic meaning when it captures the percentage change in one variable upon the other variable.
No, impulse response does not have economic interpretation if you are using impulse response calculated using reduced form errors. So I explained first, which any var can be written converted or inverted into a moving average process. Reduced form or var also it can be expressed as a function of reduced form errors. So if you use impulse response from reduced form errors, then it doesn't have any economic meaning. So that only we need to recover the structural errors. So you need to express the impulse response or structural, you have to recover the structural impulse response. So you should be able to write the var in terms of structural errors. Then that impulse response makes sense. So if you are using reduced form errors impulse response function, that doesn't make any sense. That's what I meant.
Fine. Okay, sir. Okay, so then
Bye.
Yeah, just a minute.
I would like to take this opportunity to thank Dr. Sunil Paul sir for this marvelous session, which was insightful and illuminating. I'm sure this session cleared up a lot of avenues of questions which arose in yesterday's session on univariate time series for the participants. The session today, no doubt, will help us understand the macroeconomic aspects better. With that, we will be concluding this session.
Thank you.
Yeah. Thank you, Sunil. Just a minute. Participants, Raja sir already joined, so try to join in time. He sir was already connected. Okay. So maybe take another 5 minutes extra. We'll start by 11:35. Okay. Thank you, Sunil. Thanks for your time and
sir. Thank you.
lecture. Sir, good afternoon, sir.
Tell me.
Balaji?
Number plus
Sir, very good afternoon, sir. Can we start, sir?
Yeah, I'm
Okay.
here.
Okay, sir. Induja, you can proceed now.
Am I audible, right?
Yes, sir. You are loud and clear, sir.
Okay, fine.
A very good morning, and I welcome you all to the 7th session of the online FDP on data analysis. I would like to welcome our speaker today, Professor S. Raja Sedudure, sir, professor at the School of Economics, University of Hyderabad. We had a wonderful session with him yesterday on the topic time series models, a preliminary understanding. Today, we will be continuing on to the session by sir on co-integration models. Without further ado, I invite Professor Sedudure, sir, to start our session.
Thank you, Induja, for your introductory remarks. But okay, anyhow, this will be again an extension of what we have seen in the last session, yesterday's session. So I'm going to continue with the co-integration models. So it's nothing but an extension of the random process and random walk processes, which we discussed yesterday. Okay, so see, you might have learned by this time that the ARIMA modeling and WAR modeling, where predominantly we use the stationary process. Okay, so if a process is a non-stationary process, then we need a different set of tools and techniques to analyze it. So one of the famous and interesting tools available to analyze non-stationary process, which is random walk process, is co-integration techniques. Okay, so what I am going to do today is same as what I have done yesterday. So I'm going to give you the basic understanding, intuitive understanding of. Am I audible?
Yes, sir. You are loud and clear, sir.
Okay, so the intuitive idea behind co-integration, okay, and then how to run a co-integration and how to interpret these results. See, if you understand the intuitive idea behind it, then it is very easy for you to do the analysis. So the focus should be on giving you the intuitive idea. I'm not going to, even though I'm going to show you some mathematics, but I'm not going to elaborate on that. But I just want you to get the gist of the intuition behind it, and then you have to read upon so that you get further clarity and okay. I hope okay. So I have not shared my. I'll share my screen first. My screen.
Yes, sir. It's sharing, sir.
Okay, so this things are. Give me a minute. I'm trying to make it as full screen. Okay. Fine. So before going into the concept of co-integration, I actually want you to go back and have a idea about the matrices. Okay. So this is, matrices are part of our life from our school days. We will be using this and also in econometrics particularly, if you apply matrices it helps us in many ways. Okay. So first we'll understand what a matrix is and how it helps in understanding these techniques. See, why I am introducing matrix here, the intuitive idea behind the concepts of matrices is that most of our analysis, okay, so if you see in econometrics, most of the analysis are done with two types of matrices. Okay, so one is correlation matrix and another one is variance covariance matrix. Okay, most of the time these matrices are a square matrix. Okay, so both the correlation matrix as well as variance covariance matrix are square matrix. So the square matrix has its own characteristics, and if you understand the characteristics of matrices and the idea behind matrices, the usefulness of matrices, then it is very easy for us to understand the techniques which we are going to see today. Okay. As I told you, you have to keep in mind two matrices, correlation matrix and variance covariance matrix. If you see in most of the econometrics, we use these two matrices for most of the analysis. Okay. Okay, so we all know that matrix is actually arrangement of variables and in row and column. See, if we have an equation like this, three variable equation, three unknowns and three equations, so it is easily solvable. You can algebraically solve these equations. You can also mathematically solve. Okay, so solving through matrix is much simpler than solving it through algebraically. If you have a bigger set of equations. Okay, so here three unknowns, three equations, fine. If you have 30 unknowns, 30 equations, then solving it algebraically requires some amount of computation. Okay, but if we present it in a matrix form, then it becomes much easier. So what I do here is that I'm actually, I hope you see this. The same equation has been written in matrix form here. Okay, so now what happens is that all we need to solve this equation is that we need to find out the inverse of this matrix. So you have to keep one thing in mind. In matrix, only summation, subtraction, and multiplication are there. And there are two types of multiplication in matrices, but there is no division in matrix as such. But instead of division, we have a concept called matrix inverse. So what we do is that rather than taking this matrix to this side and divide it with this matrix, we do what we usually do in matrix is that we have to multiply it with an inverse of this so that it becomes an identity matrix. And then the same, if you multiply it with an inverse of it here, you can solve this. Okay. So the only thing here is that rather than even if you have a 30 by 30 matrix with 30 equations and 30 unknowns, all you need is to do a matrix inverse. See, even though calculating matrix inverse with pen and paper manually is little complex. That we can't avoid, but with the advent of computers and calculators, it is much easier. And also the other advantage of matrix is that it simplifies the equation representation and all those things. So that is the basic advantage of that. But forget about the use of matrices as of now. I have actually a different question here. How to visualize a matrix? Okay, so if I want to make a graph out of matrix, how to do that? Can we visualize matrix? So that is actually the thing we actually want to understand here. Say, for example, if you have an equation like this, y is ax. Okay, so if y is a vector and a is a constant and x is a vector, then it is simply a straight line or linear relationship. So for the set of values of x, we multiply it with a to get the values of y. Okay, so it is very simple. If it is a vector, y and x, vector is nothing but a form of matrix only, but with one column or one row. Okay, so it can have n observations, then it becomes n by 1 matrix or 1 by n matrix. So if it is a single row or a column, we call it as a vector. But if it is a set of rows and columns, then it becomes a matrix. And if the rows and columns are equal, then it becomes a square matrix. Okay. So if we have an example like this, if y and x are individual values, a vector, have something like this. So if the values of x varies from 0 to 10, then correspondingly you can compute y value from this relationship and you get the y value. So this can be graphed like this. Okay, so all these points here represents the pair. Okay, so this is 0 and 0 and this is 1 and 0.5. So 1 x value and 0.5 y value. Okay, so this is the visual replication of this particular equation. Okay, so now fine, this is good. But if y and x are a matrix, okay, if it has n by 2 matrix y and x is also n by 2 and a is also a matrix. Okay, so here this particular a is called as transformation constant or transformation parameter. Okay, so if we have something like this, okay, x vector as like this, okay, and we have a which is again a square matrix. It's a transformation matrix. So then I'll get a y like this. Okay, so if I multiply x with this transformation matrix, the result. So the question here is how to make a graph of this. Okay, so what I'll do, I'll go back to Excel and show you how to make a visual effect of this. Why I am showing all this is that we are going to learn about two important things which has been frequently used in econometrics, which are called eigenvalues and eigenvectors of a matrix. Okay, so we have to understand intuitively what this eigenvalues and eigenvectors mean. Okay, so eigenvalue represents something and eigenvector represents something. If you have a basic idea about these two concepts, then understanding co-integration or any other things which actually coming out of this eigenvalues and eigenvectors will be very easy for you to. Okay, so here we have to keep in mind that in that particular case where y and x are vectors. It's a two-dimensional graph. If it goes as a vector matrix, then the entire dimension changes. Matrices are actually in the space. We can't visualize it in a two-dimensional space. We have to do it in three or more dimensional space. Okay. See, another point we have to keep in mind is that we can only have three dimension because our visual capacity is only limited to see three dimension, and fourth and fifth dimension we can't imagine. Okay, we can't visualize. That is due to our own constraints. So the mathematics helps in doing that. So once we understand these things, so that the maximum visualization can be made in a three dimension. Okay, beyond that, we all use mathematics to understand. Okay, so all of you know that eigenvectors and eigenvalues. See, this is a theoretical part of it. After I show you how to visualize a matrix and what this visualization means and how we can and what these two values, eigenvalues and eigenvectors, is representing. Okay, so for that I'll go back to Excel. Can you see my Excel sheet?
Yes, sir.
Yes, sir.
It's visible.
So now this matrix, okay, has been plotted like this. Here, this is X matrix. Okay, so we'll come to the Y matrix later. It is only the X matrix. Okay, so all these points, 0, 0 is pointed here, 1, 0 is pointed here. Okay, so it's a two-dimensional matrix. So don't consider this as Y and this as X. If it is a two-dimension matrix, means what? There are how many rows there? So we have 49 rows, and we have two columns. Okay. So all these points are actually the representing what is there as a pair. Okay. So it represents. So if it is a three column matrix, then it becomes a three-dimensional map. Okay. So if it is a 4-column matrix, then you can't visualize it, but you can understand that. So it is a 4-dimension. It operates in a 4-dimension space. Okay. So what I have done here is that I am just simply plotted all the X values here, whatever there in X, okay, has been given here. So now we have it's a 6 by there are 7 values including 0, 7 by 7 matrix. So we have 49 values in that. Okay. So now if I want to write an equation like this with an matrix transformation matrix. So I'm taking a very simple transformation matrix here. See, these two are actually to find out the eigenvalues. So forget about this part for now. See, finding out eigenvalues and the eigenvectors are much simpler now once you understand the concept. Okay, so if this is the A matrix, the transformation matrix. So if I multiply this with this, I'm going to get this Y matrix. So what I am doing is that, so every row I am multiplying with this matrix, the resultant Y matrix. Okay. Since we have identity matrix, Okay, this is an identity transformation matrix. The Y will also be identical to X. If I use an identity matrix to multiply it with any matrix, the resultant matrix will be the same matrix. Okay. So that is actually coming here. So what I have done here is that I have plotted both these values. Okay. So this graph is only the X matrix, and this one is actually, having both the matrix. Okay. Now, if I change, see, since it is identical matrix, because we have given identity matrix here, um, it looks same. So it is same. So the Y matrix is actually behind this X matrix. So once I change this matrix, say for example, instead of 1, if I make it as 2, okay, so now you can see the resultant X and Y. So this is the X, the original matrix, and this is the Y. Add with 2, it expands like this. Okay, so up to 12 here, up to 12 here. So it has been doubled. So you will get matrix. The transformation matrix, what it does is that it actually, changes the shape of the resultant matrix. Okay. So now, if I have another value here, so instead of identity, this is identity matrix, it is simple multiplication with a value. So 1 means same, 2 means 2 times the matrix, 3 means 3 times the matrix, like that. But if I'm going to give a totally different matrix here, if I give this matrix, okay, so if you see the you see here, so it has been an elongated matrix, right? So what happens here is that one side has been elongated. Okay. So one side remains same because of this one. Other side is elongated. So whatever change happens in this, if I give a minus value here, then it flips, matrix flips. So the basic idea here is, if there is a matrix multiplied with a transformation matrix, the resultant matrix will take the shape according to the transformation matrix. So, you can play around with this. So if you change this value also to -1 or some other value, you can see that the resultant matrix flips. So, interesting question is what this eigen vector and eigen values. So, this is actually if you want the theoretical reasoning, I'll give that later, but I actually, the calculating the eigen vector for a particular eigen value for a particular matrix is using this particular equation. Okay, so TR is trace. Trace is nothing but anyhow. So if I calculate this, okay, so trace is summation of the diagonal values. So what I have done here is that I'm calculating the eigen values of this transformation matrix. So the first eigenvalue will be trace of A, which is D4 plus E5. by 2. So it is summation of the trace is nothing but the summation of the diagonal. Okay. And then, so if you simply use this equation and the determinant of A, then you will get 3. And another eigenvalue will be 1. So 1 and 3. So what it means is that if the eigenvector of any particular matrix is 3 means the matrix has been pulled upon or elongated 3 times. Okay, so the original value is 6 here, but it has been elongated till 18. Okay, so 3 times elongated on one side. The other side, it remains same because the eigenvalue is exactly 1. So which means that the other side shape is not changing. The other side means this side. Okay, so this side remains there, but only this side has been pulled 3 times. Okay, so what the eigenvalues do here is that it tells you about how the transformation matrix changes the shape of your original matrix. Okay, it is as simple as that. Okay, so you can try it with some other value. Say for example, you just put 0.5, and so one side it has been elongated 2.5 times. So you can see that it is 2.5 times. Okay, so 6 into 2.5, it will be 50. And this side it is elongated 1.5, so it will be elongated from 6 to 9. So the eigenvalues simply tells you how a original matrix has been elongated or shrinked. Okay, it can also shrink. Okay, so if you have 0.2 here and 0.2 here, so now it's shrinked. The original matrix and the resultant matrix has been shrinked by this proportion. So this is the story about the eigenvalues. We'll come to the eigenvector. Okay, for that, see, calculating eigenvalues and eigenvectors are easy. In Excel, there is a tool for that. So there is a function. You have to download this tool. So if you simply type eigenvalues and eigenvectors in Excel, you will get a tool here, and you download it and install it in your system. Then you'll get these two functions here. Okay, the same thing. So whatever. So this is the and this is the eigenvalues, or you can calculate it like this using this formula. But you have to calculate the eigenvectors like this. I'll come to the eigenvectors part. A different example to understand the eigenvectors. Values are nothing but how the original matrix has been transformed. Okay, so the eigenvalues will tell you sprint on each side. So that is the intuitive interpretation. What eigenvectors are doing, see, technically eigenvectors and eigenvalues of a matrix A are defined like this. Here the lambda values are eigenvalues and X are called I don't want to explain how to identify these things, and see you can also, you might have heard decomposition called Cholesky decomposition. So that is basically trying to identify eigenvectors. I'm not going to that, so this is not about understanding eigenvalues and eigenvectors. Okay, so but you have to get an intuitive idea so that you can really enjoy the beauty of mathematics. Okay, so to explain eigenvectors, I'll give another example. If there is two restaurants and there are 1,000 customers every week for these two restaurants. Okay, now 80% of the people who buy biryani. See, I put Hyderabad and biryani because of my place of living. Okay, so 80% of the people who buy biryani each week at A is written the following way. Okay, so what happens is that there are two restaurants offering biryanis in the city, and the customers who come to A, 80% of them are coming back again. Okay, means what? 20% are not coming back. They are going to the B restaurant. This is the story for B. 40% of the people who buy come back. So 80% and 40% are the repeat customers of A and B. Okay, so the rest of the customers go to the other restaurant. 50% goes to other restaurant, but 60% of B is coming to A the next week. Okay, so this is it might go on for if I want to know how much customer will be there after 10 weeks, I have to do the calculation, right? So that is what we are going to do. That is where this eigenvectors will help us. Okay, so now the customer for the next week, which is week plus 1, is nothing but the transformation matrix, which we will design now, and the customer who is coming on that particular week. So here the transformation matrix is like this. So here 0.8 is the repeat. See, this is A and B, and this is A and B. Okay, so you keep A, B here, A, B here. So A, 80% come back to A, and 20% goes of A customer goes to B, and 60 of B comes to A the next week, and 40 come back to B itself. So this is the transformation matrix. And if there is 1,000 customers in the market, then we have to multiply these two things to get the resultant after. So I'll go back again to Excel to show you what is happening there. Okay, so this is the matrix, transformation matrix for that biryani example. Have 1,000. Okay, or see, this is 1,000. I'm starting with. You can also start with any number. Okay, so you can start with here. Customer. This is a new restaurant, and 1,000 is there in B. So then people might shift with this transformation. Okay, so we'll start with the simple thing. So each restaurant have 1,000 customer first, and then we have to see what happened after. Okay. So this is the matrix, and then this is the eigenvalue of this matrix. So what the eigenvalue tells you is that the resultant matrix will shrink by this much. One side is going to be the same, and one side is going to shrink. It is not going to elongate. It is going to shrink because it is less than 1 here. So forget about that part, because we understood what eigenvalues are here, but we are more concerned about the eigenvectors. Okay, so eigenvectors is this. So if I multiply this with this and this with this, I'm going to get the same matrix. So that is what this particular formula. Yeah. Yes.
Sir, using the transformation matrix, sir, in the Excel file, sir, using the transformation matrix, how do we get these eigen values?
Yeah, that's why I already told you there is two ways. One is you can use this formula to get the eigenvalues, or there are a lot of tools available in Excel. Okay, so what I am going to do is that there is a function called eigenvalue. I give this. These functions are add-on functions. You have to download and install it in your Excel. So there are plenty of add-on functions available free of cost, which can be added to your Excel so that a lot of things can be done in Excel. Okay. So otherwise,
Sir,
you are to the.
In this case, the 0.8 and 0.2 are added, and then the first eigenvalue is there 1. You said that. That is the trace.
See, yes. So you will get eigenvalues in the trace only. Okay, because if it is a 2 by 2 matrix, you will get 2 eigenvalues. 3 by 3 matrix, 3 eigenvalues, like that. Okay, and so if it is a 3 by 3 matrix, then it will be 3 values, and the rest of the values will be 0. Okay, so what I am trying to say here is that don't go deeper into the mathematics part of it. It is available in, see, we are living with matrices from I think 8th standard. Okay, so it is there from the 8th standard textbook. So I don't want to go much into the mathematics part of it. But what is more important here is the intuitive part of it. Okay, so what eigenvalues represent here is it only tell us the shape of the resultant matrix. Okay, so there is a X matrix and the transformation matrix and the resultant matrix Y. So eigenvalues will tell us what is the shape of the resultant matrix. So if I get 1 and 0.2, which means that one side remains same, the other side has been shrinked. Okay. So if you want, you can plug these values here and then see how the matrix looks like. Okay. If you want, I can do that as well. This using the formula, but this is how it looks. So this is the input matrix, and this is the resultant matrix. It has been shrinked by 0.2. One side remains same. Okay, fine. We'll move on to the vector. Okay, vector is again you can calculate using as I said you can use Cholesky decomposition to derive the eigenvectors. But otherwise, you can any standard will give you the eigenvectors of the matrix. Okay, so mostly this can be done only for the square. So now I'll come back to the example which I am giving. So this is the transformation matrix, and this is the this is restaurant A, this is restaurant B, and B here. So this is repeat customers. This customer goes to B. This is repeat of B, and this customer goes to A. What is the resultant next week? So I'm going to multiply the transformation matrix with the X matrix. Okay, so sorry. ML is the matrix multiplication in Excel. So 80% means 800 comes back, and 600 from B also comes back. So it is 1400. In this, for the case of B, 400 of their own customer come back, and 200 from A is going to join them. So 6. This is next week. Next to next week, I want it for 10 weeks. So what I'm going to do is that I'm going to multiply this resultant with the same matrix. If transition matrix remains same, okay, so I can keep on doing this. Okay, you have to do it 10 times to get the 10th week, but I'll tell you that is not required after a point. On doing this, one more point I'll do, and then I'll stop. In this, what you will get is ultimately, you'll get something like this. 500 and 1,500 for restaurant A and 500 for you can do it for multiple times. Even if you do it for these things, this value is going to remain same. Okay, so what happens is that even if you change this to 0, this becomes 750 and 250. Means the ratio is end of the thing, the ratio is this. Okay, so 3. Eigenvector actually represents is that. So think about the eigenvector which is coming here. What you have to do is that you have to take the ratio of these eigenvectors. Of this is 3 and the ratio of this is. So what the eigenvector represents is that if this goes on for multiple times, the long run or the long term consistency will be of this 3:1 ratio. Okay, if I put a negative value here, and you can get this -1 here. So what these ratios from the eigenvector represent is that it tells you the transformation matrix and the relationship with the resultant matrix in the long term. So how this relationship is going to, what is the ratio in which these two going to converge. Okay. So eigenvalue will tell you the shape of the resultant matrix. Vector will tell you in the long term how this relationship is going to stabilize. Okay, so I think this is enough to understand these two things. So eigenvalues and eigenvectors are used here predominantly to understand these things. So this is a graphical. I don't want to discuss this. Okay. So we are going to use these two concepts more in integration analysis or any other. If you might have worked already in Johansson co-integration, you might have known about these eigenvalues and vectors. This is the intuitive idea behind that. Now we'll shift to the main focus of today's lecture, okay, which is co-integration. So time series data, we already discussed in yesterday's class. is only the realized value from a set of probable values. Okay, I give an example of Ford production capacity and the production output. Okay, so the capacity is the set of probable values, and actual production will be the realized value of that. Okay, so time series we look like that. So what we get as a value for a particular time period is the realized value, which means that behind that realized value there is a set of values, probable values, which has been generated by the data generating process. Okay, out of it, one realized value will be coming at that particular time. Okay. So whenever you see a time series data, if you understand this well, so it's a realized value coming out of a process. So the stability of the process is actually the main concern in the time series analysis, and the understanding of the process is the main concern in time series analysis. Once we understand this, then the rest is simply the building upon these understanding. Okay. So the focus is mainly on the data generating process rather than the data. So whenever there is an inflation data, okay, fine. From common man point of view, the number, the realized value is of more important. But from a economic analysis point of view, we have to understand what DGP, the data generating process, which has created that realized value. Okay, so there are theoretical process. This I have already explained it to you. We have stationary process and non-stationary process. Okay. See, I told you white noise is same as stationary random process with a specific randomness. If the random process has a mean 0 and variance 1, then we call it as a white noise process. Any constant mean and constant variance is also called a stationary process. So all the other, so the specific case of 0 and 1 gives us a different name, but all the constant variance and constant mean processes are all stationary process. The random walk process again is nothing but the cumulative sum of the random process. The cumulative, that sum coefficient will be exactly equal to 1. Okay, so if the sum coefficient is less than 1, then obviously it's not a random walk. It again random process. So random walk process is an extension of random process only, where the cumulative sum coefficient becomes exactly equal to 1. Okay, if it is -1 or greater than 1, it gives a different process. We are not going to discuss about all this, but every other process has its own application in other sciences. Okay, so, but in economic science, we use mostly these two processes. Okay, so this I already explained, so I don't want to again indulge in this. Okay, so fine. This is an argument. This is a Dickey-Fuller test, and this is an augmented Dickey-Fuller test. So what we test is this is 0 or not. Okay, if it is 0, then the process is random walk. If it is not 0, then it is a stationary process. Okay, now, so if it is stationary, okay, fine. We have plenty of techniques to implement, starting with ARIMA modeling, Granger causality, and pair modeling. So all these things are applied to those variables whose data generating process are a stationary process. Okay, and the interesting thing about a random process and a random walk process is that if you take a first difference of a random walk process, it actually converges back to random process. So in that case, most of the time what we do is we convert the random walk process into a random process and then apply all these things. Okay, Granger causality or VAR or whatever tools, and then we can interpret. But the thing is that once it comes as a random walk process, then we have to understand whether there is any commonality between multiple variables. Okay, so the co-integration uh, is all about identifying this commonality. Okay, so what I mean by commonality is that I'll go back. See, this is full of equations. I don't want to do this because you'll get lost in these equations. But intuitively, I'll show you what co-integration means. Okay, so we'll go back to. I hope my Excel is visible.
It's visible.
Okay, so as I explained it to you yesterday, what I have done here is that I have created a random process. Okay, so random process, how to create it is not created. It is like picking some randomly some numbers from the normal distribution. Okay, so here, if you put a S here, then it picks from standard normal distribution, or you can pick a random number from the normal distribution whose mean is 0 and the standard deviation is 1. Okay. So what I have done is that I have created a random process. Okay, so there are how many data points? 250 data points. Okay, so since it has been created for every click, it different numbers. Okay, so it's a random process. But here, what I have done is that I have made a cumulative sum of this random process. What I have done is nothing but I simply added this with the new number. So I'm summing it cumulatively. Okay. So where the summation coefficient is exactly 1. Okay, so I'm creating a random walk process out of a random process. Okay, so this is actually the random walk process from this random process. So the corresponding cumulative sum is looking like this. This is a set. There is a random process and there is a cumulative sum of it. So this is a random stationary and this is non-stationary. Now I'm creating another set. Okay, so this is totally an exclusive random process which has no relationship with this. Okay, it's a very exclusive random process. So I'm creating it separately. So the same kind of thing. So where the mean is 0, but the standard deviation is 0.5. To give some difference, I'm slightly modifying the standard deviation and then giving the generating the series. Now this is the cumulative sum of this random process, which is x. Okay, so this is the cumulative sum of this. Again, the cumulative sum coefficient is 1, so which make this as a random walk process. Okay, so for every click you will get a different value. Okay, now, so what see, there are two different random walk process originating from two different random process. Okay, so nowhere it is connected. So there is. Okay. So if you take a correlation between these two, okay, you can get very less totally exclusive random process. Okay, so if two exclusive random process has created a random walk process, then there is no relationship between these two cumulative sums. Okay, but you can also make a random walk process as a function of this. Okay, so here what I have done is I have created only one random process and taken a cumulative sum here. Okay, and then I'm creating an XT not from an exclusive another random process. What I am doing is that I am going to take this cumulative sum, okay, but with a transformation. I'm going to use some intercept or constant value plus 0.5 times this cumulative sum and also add some error terms. But the basis is coming from the cumulative sum of YT. Okay, so this is nothing but a transformation of this from this particular cumulative sum. Okay, if that is the case, okay, so if both these, this is actually the YT and this is the cumulative sum of YT, and this is actually the transformation of YT with some constant and all. Okay, so the error, you can see, will be the difference after running a regression between these two and taking the error, this error will look like, yeah. So this is exactly what cointegration means. Cointegration, what it means is that we are trying to see whether two random walk process are originating from the same random process. Okay, so that is the basic. Is originating from the same random process, and we call that these two are cointegrated. Okay, this is like, you know, siblings. Okay, so the mother remains this YT. These two are actually outcome of this random process. Okay, so now here the Granger type cointegration is, see, the entire idea of cointegration has been originated by Granger. What he identified is that if this is the case, then obviously the difference between these two, the error. Okay, so if I see, this is nothing but the transformation, right? This part. Okay, what remains there is nothing but the random process. Okay, so if the random process is the resultant, if I remove the transformation part from the original thing, then, you know, remaining thing will be a stationary process. So after running a regression, if the error becomes stationary, he said that these two are co-integrated. What it means, it is actually originating from the same random process. Okay, and there is, I hope it is clear now. So what we are trying to do here. Okay, so now if there are two variables, random walk variables, then there will be only one relationship, because this is the original cumulative sum and this is the resultant transformation of this series. Okay, so here this transformation vector is called the cointegrating vector. Okay, so now ultimately, you know, this we have created it and we know that this is the transformation. Okay, so now this is kind of simulation. So we create a random process, cumulative sum, and then create another series from that cumulative sum. And we are saying that, okay, fine. If we know that this is created from this, so it is cointegrated. But in this case, it is mutually exclusive. This cumulative sum is not originating, or we can put it in another way. these two random walk process are not coming from the same random process, then it is not going to integrate. Okay, so that's the basic premises in which the entire idea of integration has been built on. Okay. Now this transformation is called the co-integrating vector. So what I have done here is, so we have already given 2 and 0.5 here. So that becomes our co-integrating vector. Okay. And this will now the thing is that, okay, fine. In real world, what happens is that if there are two variables like this, we don't know whether from where it has been originated. Okay. So what the simple Granger type co-integration technique is trying to do is that he says that, if you have two random walk process, okay, so don't do a regression and try to interpret the coefficients, because it becomes a spurious regression. Okay, first we have to see that whether these two are originating from the same random process. Okay, which means that we have to see that whether these two are co-integrate. Okay, so for that, what he is suggesting is that we have to run a regression between these two variables first. So this will be the coefficients, and then the resultant error, if it is stationary, then we can say that these two random walk process are co-integrated. Okay, so in real world, we are going to have multiple variables. I'll give another example also. We are going to have multiple variables. The idea of co-integration is that to understand whether it is originating from the same random process. Okay, so if there are some 4 or 5 random walk process variables, okay, coming from two random process. Okay, so this is, see, this y and xt comes from same random process. If you have another set, which actually comes from another random process, there now we have 4 variables. Okay, so if these are co-integrated, okay, then we see the whole idea is that how many random process are generating this random walk process. So the main aim in this is to understand the origin of this random walk process. Okay, so that's the basic idea. So the simplest co-integration test is Engel Granger type test, where you simply run a regression and see whether the errors are stationary. If the errors are stationary, then we can say that these two are co-integrated. If it is coming from totally different random process, then obviously the errors won't be stationary. Okay. Hope I'm audible. I'm there online.
Yes, sir.
Sir,
Okay.
clear and good, sir.
So
Yes, sir.
now we'll.
Hello.
I hope you people understood what I am trying to say.
Hello, sir.
Yeah.
Yes, who's this?
Sir, in
Yes,
the
yes.
Excel file, can you please go to the Excel file? Sir, in the DGP sheet, sir, the correlation is very much less.
Yeah, because both are mutually exclusive.
Mutually exclusive. Then we can say that co-integration cannot be applied in this case.
Yeah, no co-integration. Here in
No
DGP, no co-integration. But here
But
in
there is
this,
a co-integration.
yeah, so I am having only one random process, and I am creating two different cumulative sum of it. So one is the actual cumulative sum with the cumulative coefficient 1, and another series which is a transformation of the cumulative sum. Okay.
Which depends on the cumulative sum.
Yeah. Yes.
And that is why there is a correlation.
Yes. So that is why we call these two are co-integrate. See, co-integration is nothing but to identify whether they have any relationship. Okay. So the relationship in more theoretical way, how we can identify is that whether they are coming out of the same random process or not. Okay. So if they are coming out of the same random process, see, it is, if you want to keep a simple analogy, we are going to test whether YT and XT are siblings or not.
Sir, there
If
is a
they are
question
coming from the,
further.
yeah.
Sir, if this is a simulation, we are having a sample and run this correlation and found it like 0.5, say, for the first value. It is
No,
0.5 for the first
this is
given.
actually, no, this is actually the regression coefficient. So what I have done here is that I have run a regression. So that is what the Engel-Granger type co-integration test is trying to do. If you have two random walk process, you run a regression, and then using that parameters, you can actually take the errors and see whether the errors are stationary. If the errors are stationary, then they say that these two are co-integrated. So that is one type of test to identify the co-integration.
So whether it is statistically significant or not, how can we test for that?
That, see, that's the idea, because definitely it will be statistically significant because it is a simulated data. Okay, so I am simulating it 2 plus 0.5. It is exactly getting me the numbers. So if you run a regression with data analysis, you will get a statistically significant thing. But again, yes, I'll agree to your question that we have to interpret with statistically significant parameters. Okay, so if it is statistically significant and the errors are stationary, then we can confidently say that these two are co-integrated. Okay, you can also run a reverse regression, keeping X as independent variable and Y as independent variable, and do the same thing. Okay, so in Engel-Granger, there are some issues in that. Okay, so I'll explain it to you in the coming slide.
Sure.
Okay, so but the basic remains same. The basic idea is to identify the mother. Okay, the mother is same, then we say that these two are siblings. Fine, that's the intuitive idea to understand co-integration. Okay, the problem is that, see, if there is another family, okay, where we have another random process, random walk, cumulative sum, another transformation. Okay, if you put everything together, YT, XT, and ZT, and whatever is coming out of another family also, that will also, the Engel-Granger type co-integration is that it will tell that because this has created this error, another family will also create another error. Again, it's a stationary. So if you put everything together also, the error will become a stationary variable one. Okay, so the problem here is that still we say that these are all co-integrated, but might be they are co-integrated separately. Okay, so that is a much bigger issue to understand in the co-integration analysis. But to start with, this is the basic intuitive idea of what the co-integration technique is trying to address. Okay, it is trying to trace whether two series of random walk process coming from the same random process or not. That's the basic idea. Okay. Okay, so if you want to see some mathematics, this is the thing. So all the components XT are integrated of the same order. Okay, because why this is because the xt in the example has been derived from yt, which is a cumulative sum. You can make another cumulative sum also. So I actually we can also have one more cumulative sum of this the cumulative sum. Then it is actually 2 times cumulative sum. So then we have to difference it twice to get the original random process. Okay, so the order of integration tells you all about how many times we have executed this cumulative sum. Okay, so if it is 1, then the cumulative sum is 1. If it is 2, then the cumulative sum has been again summed to get the series. Okay, so see, in most of the cases, we don't go beyond 1 or 2 because most of the economic variables become stationary or with the second difference itself. And make a series, multiple differences like 5 times differencing and make it as stationary has no meaning. Okay, so it should be either, the maximum should be the second difference, but not beyond that. Okay, so all the components of xt are integrated of the same order. If it is different order, then again, if one series is integrated of order 1 and another series is integrated of order 2, then we need a separate technique to analyze those kind of variables. But what we are going to see here in co-integration is only with the similar order of integration. Okay. So there exists a vector. This is actually the transformation of one random walk process to another, such that linear combination is integrator of order 0, which means that the error becomes 0. Okay. So, sorry, the error becomes stationary. So the order 0 means it's a random process. Okay. See, all these things, it's all same. If you hear the word integration, it is nothing but summation. If you hear the word differentiation, it is nothing but subtraction. Okay. So there are standard vocabulary used in maths, so it gives same meaning everywhere. So the vector v, that transformation thing, so in the example 2.1.5 is called integrating. Okay, so I'll give an example. This is quantity theory of money, which has been defined like this. P equal to Py, where M is stock of money, velocity in price level and output. Okay, so in reality, if you go and collect data, these variables are a random walk process. Okay, and velocity is a constant. So hence the time series on these variables are not mean reverting. Okay, however, theory asserts that there exists an equilibrium relationship, hence a combination of these non-stationary variables may be changed. Okay, so here, if these variables are co-integrated, then we can say that it is coming out of same stationary process. Okay, so then we can say that there is an equilibrium relationship exists between these variables. If it is co-integrated, they are related. They actually formed on the same premises, so we can say that it has an equilibrium relationship. So if you tinker one, the other will change. So that is what we mean as equilibrium relationship. Even if there is any deviation because of some random event, it will come back to the equilibrium position. So that is how it is interpreted. So the above equation again, asterisk to be constant. Okay, so this is again see the interesting inference or the point we have to keep in mind here is that in real world we can't get the that co-integrating relationship because see this vector is not the this vector is nothing but the transformation relationship of one random walk process to another random walk process. Okay, so don't get it confused with the eigenvector which we have seen later. That eigenvector and eigenvalue will come in Johansson type co-integration. Okay, but the point here is that we don't in real world data we don't get the you can say a unique co-integrating vector because these are all constants, right? All the parameters. So any numerical transformation of these constants will also give you error, which again be a stationary variable. Okay, so whatever be the value of this, see instead of this value 1, 2, 3, and 4, if you give 2, 4, 6, and 8 also will give you the same properties for the error. So the co-integrating vector is not unique. Okay, and also it is very difficult to identify the exact co-integrating vector if there are multiple variables in the system. So you have to normalize it. So we will extract a possible relationship, but I'll give you with one more example. I'll show you, then you can understand easily what I mean by normalization of this co-integrating vector. So the error here actually measures the short-run deviation from the identity. Okay. Any short-term deviation will be, coming back or converge after a point of time. The whole idea of this co-integration and error correction model. Okay, so see this relationship, even though it is related, there might be some random errors possible to appear. Okay, so that is actually deviation from the equilibrium, but it will come back to the equilibrium after a point. So how quickly it will come back will be given by the adjustment parameter. I'll show you that part also. Okay. So the first thing we have to keep in mind is that if the error becomes I0 stationary, then there is a co-integration, and the regression vector will be the co-integrating vector. Error is a temporary deviation. If I put that error into a vector error correction model, okay, which is, a vector error correction model is nothing but to take the first difference of all these variables and then make a var. By adding the error also into that var, then it becomes a error correction model. So there it will tell you how much, what is the speed of adjustment, so of each variable to come back to the equilibrium. Okay. Integration vector is not unique. See, that is what I already said. Then we have to normalize it with some particular thing. So usually we normalize it with the first variable. So make that variable as 1, and then normalize it by dividing that with other coefficients. Then we will get the normalized vector. Okay. So here, the whole idea is that even though co-integrating vector plays some role in some analysis, the main purpose here is to see whether there is any co-integration between variables and what is the adjustment parameter. So it is all about identification. Okay. If there is n variables, there could be n minus 1 co-integrating vector. So as we have seen in the example, there are two variables yt and xt, and there will be only one co-integrating vector because xt is a resultant of yt. So if there are 5 variables, then there will be possibly 4 co-integrating vectors because one will remain as the basis. On that only, no others are derived. Okay, so this again, the same thing. So if we include this error into the vector autoregressive framework, then we call that as a error correction representation. The entire system is called vector error correction models. Okay. So if you see that since every variable MP and Y are I1 variable, I am taking the first difference and then setting up a var like this by including the past value of the error term coming out of the co-integrating relationship. Right. So these parameters are called adjustment parameters. Okay, so that will tell you that how fast this particular variable will converge to equilibrium if there is any deviation from this equilibrium. Okay. There is any disequilibrium in the previous period, how variables are adjusted to the equilibrium. So the speed of adjustment is captured by these variables. Okay, so this will be independent, and see if this is significant, then we can say that there is a speed of adjustment. If it is insignificant, the speed of adjustment is insignificant. This is one important point you have to keep in mind. If it is insignificant, then we can be very sure that this particular variable is the basic variable. Okay, based on which the other two variables are derived. Okay, so the original random walk process is this, if their adjustment parameter is insignificant. Okay, so all the other two are derivation from the original random walk. So there is an adjustment parameter, significant adjustment parameter to the deviation, because this is the basis. These two are derived, so obviously these two will react. Okay. So again, this inference will help us in identifying the causal relationship also. Okay. So if in our example, xt, the random walk process has been created from yt, which is the original cumulative sum. Okay. Then in that case, even though these two are co-integrated, we can say that y is causing x, not the other way around, right? Because x is derived from y. So whatever change happens in y will be affecting x, not the other way. So, the entire causality framework will be changed if we have a random walk process in the system. Okay, so the entire interpretation, modeling will be totally different if the series is a random walk process. Okay, so if all the adjustment parameters are 0, then what it means is that every random walk process has been originating from an exclusive random process. So there is no co-integration exist between these things. Okay. So this again I have already mentioned. So the Granger co-integration method, there are two steps. One is how to pretest the variables for order of the variables, and then estimate the level regression and obtain long run coefficient. Okay, so see if both y and x are I1 variable, random walk process, then run a regression like this and estimate these values. You can also keep X as dependent variable and Y as dependent variable and run. Okay, you will get us, the inverse coefficient for that relationship. If it is 2 here, then you will get 0.5 there in if you replace these values, if you swap the dependent and independent. But you'll get the from both errors you can interpret whether there is a co-integration or not. It doesn't matter which comes as dependent variable and which goes as dependent variable. Okay, so from the regression we have to get the errors and then see it's the same like the augmented Dickey-Fuller test. We have to test whether the errors are stationary or not. If it is stationary, then we can conclude that YT and XT are co-integrated. Okay. So if the null of no co-integration is rejected in the first stage, estimate the error correction model. Okay. So here, this is particularly for the Granger causality test. So usually in Granger causality, what we do is that we take a variable. If it is identified as an I1 variable, we'll take the first difference and run the causality. Okay, that is wrong actually. What we have to do is that first we have to verify that whether these two variables are integrated or not, co-integrated or not. If there is no co-integration, then fine, both are mutually exclusive. Then you can take the first difference and run the Granger causality test and interpret it. That is fine. If there is a co-integration like this, so you can't simply take the first difference and run a simple Granger causality test. We have to, do it in a vector error correction model like this. Okay. So this adjustment parameters will tell us which is causing what. Okay. So as I told you, if one adjustment parameter is insignificant, means that is the original series. So that series is causing the other series, not the other way. So that is the simple, inference from this vector error correction model. And see, once we have the errors, then we have to do all the diagnostic check on residuals for model adequacy. Okay, so Johansson co-integration, see, the same idea, but it has been for a set of variables. Okay. So Engel-Granger type of co-integration test is easy if you have 1 or 2 variables. But if you have some 5 or 6, 7 variables, then we have to run all the permutation combination to get the errors and verify. If, say for example, if for some reason in the phi equation model one error is not coming as stationary, then you have to conclude that there is no co-integration. In that case, how to interpret the whole model with that 5 variables becomes a little difficult in Granger type co-integration test. So here Johansson co-integration test is developed for a set of variables. So it is based on rank of a matrix and its characteristic roots. This characteristic roots of a matrix is nothing but the eigenvalues. So if you hear characteristic roots of a matrix, then it means that they are talking about the eigenvalues. Yeah. Okay. So this particular procedure has been if you are really interested, you can do the Johansson co-integration in Excel also. Okay, it is very much possible, provided you understand all the equations here. But forget about this for some time. what is more important is that how to run a co-integration and how to interpret these variables, the coefficients. Okay. Anyhow, the variables xt is co-integrated, then there exists a error correction mechanism that we have seen already. Okay. So how it is, constant co-integration is nothing but an extension of the for a set of variables. What it tries to do is that it runs a same equation like Dickey-Fuller equation, but for a set of variables. What is more important here is that this pi matrix, which is a combination of the adjustment parameter and the co-integrating vector. Okay, so if the variables in xt here is a matrix, a set of variables are co-integrated, then this will be a reduced rank matrix. They are not co-integrated, then it will be a full rank matrix. Okay, so if it is full rank, then we can say that all the variables in that matrix are mutually exclusive. If there is a reduced rank, then one can be written as another. Okay, so then it indicates there exists a relationship. So the rank of the matrix indicate the number of co-integrating vector. So we can get estimates of eigenvalues from the estimated value. So all you have to do is, in Excel also, all you have to do is you have to run this regression and then estimate this pi. So once this pi matrix has been derived, you can do all the further analysis. Okay, so don't worry about that, because most of the statistical softwares these days will implement constant co-integration for you and give you the required values. But what is more important here is that we have to know how to interpret these values. Okay. The two test statistics are there. One is trace and one is max. Both are actually calculated from the eigenvalues of this. I'm not going to explain all this. And this again, okay. So what this is again a causality thing, these are all the steps which I'll do is that I'll stop here and then I'll show you how to do this in statistical software, which is frequently used for. And then I'll take questions if you have any questions. Okay. So if you have any further reading of these things, there is a very famous book by Walter Enders, Time Series Econometrics. Okay, so this is actually for those people who do a lot of time series analysis, this is the go-to book. Okay, so it has all the explanation and derivations. So okay, so can you see my e-views?
Yes, sir.
Okay, so now here what I have done is the same thing. It's a kind of simulation. What I'm going to do here is that, see, this is a kind of program to the intricacies of these programs. What I am doing is that I'm first creating a work file in eViews with 500 data points. So for that, we have to do this. Or you can simply copy this and then type it in command. You get this. So there is a work file created. Okay, so all the work files will be created like this in eViews. So there are 500 observations in that work file. Okay. So now I'm going to create three separate random variables. Okay. So series X. See, this NRND is a command to create a random process in eViews, NRND. So if I create X, NRND, then I'll get this. So if you make a graph of this, you can see that it's a random process. So it will be very similar to what we have created in VXL. So what I'm going to do is that I'm going to create three separate so I can create three separate cumulative sums. Okay, I'll create three separate cumulative sums like this. Series XX is actually a cumulative sum of X. Creating that. Okay, so cumulative sum is a random walk process. If you make a graph, you can see that it's a random walk process. Okay, so the same X, if you make a cumulative sum, it becomes a random walk. Okay, so what I'm going to do here is I'm going to create three from three random process separately. So mutually, these three are exclusive. We'll actually create something which is not exclusive, and we will try to run the co-integration, Johansson co-integration in that. Okay, so what I'm doing is I'm creating two more series. One here, selecting this. X and YS. So if I run a co-integration between these three, okay, I will not get any co-integration. Okay, if you see, there won't be any co-integration, and all the adjustment parameters will be insignificant. Okay, if all the adjustment parameters are insignificant, then it really indicates.
Balaji here, man. How are you?
So it really.
Are you still? Fine, man. So you're okay, no? Tomorrow.
Balaji.
Okay, Anand. Actually, I just.
Balaji. I think he's talking to somebody else.
Yeah, just give a small note of what is DEA and what are the different procedures. Anand, actually.
Balaji. Okay, so yes, muted. Okay, fine. So this shows there is no co-integration, and all the adjustment parameters will be, insignificant. Means that all the three variables, even though it is random walk process, they are nowhere connected. But instead of exclusive cumulative sum of each of these things, so now I create two more variables which are actually coming from the same cumulative sum XX. Okay, so here I'm creating another series YS. So this is so I'll create another series like YSS. What I'm doing is that I am going to transform or derive this YSS from the cumulative sum XS here. Okay, plus some random number again, we can give that. Okay, so 2.2 plus 0.6 times XS, and Z series also I am creating like with a different combination. I am going to create like, okay, so there are three variables. Two variables are derived from the single random walk process. Okay. So now these three should be co-integrated, obviously, because these two are derived from XX. Okay. So how many co-integrating relationship? There are two co-integrating relationship because YSS have a co-integrating relationship with XX, and this also derived as a function of XX. So there are two co-integrating relationship. Okay. So if you have three variables, two co-integrating relationship, okay, then you have one random process which actually generates the other two random walk process. Okay, so that is what it means. So I'll show you this also and tell you about how to interpret these two things. Okay, so I'm creating and running a regression with this YSS and SXS. Okay. Beauty of Jorgensen is that even though this is a simulation, the beauty of Jorgensen methodology is that it will identify the co-integrating vector exactly. Yeah. So now, if you see that, you can see that there are two co-integrating relationship exist. That's the example is also saying. Okay, so this is based on the trace, and this is the based on the maximum eigenvalues. Since we have three variables, we get three eigenvalues. Okay, and if you see the co-integrating relationship here, you can see that almost it identifies the values. Okay, so we have given 2 here, so it almost takes 1.96. Why there is a negative sign? Because actually the co-integrating vector will be presented here as YSS minus 2 minus 0.6 like that. Okay, so in one side as a vector, not like an equation. So if there is a negative sign in the vector, which means that it indicates a positive relationship among the variables. Okay, so you can see that. See, since we have also given another random process here, there is a slight deviation in the numbers, but it almost traces the numbers exactly. So 0.6 and 2, here 3 and 0.2, it is there. And if you see the adjustment coefficients, okay, you can see that except XX, all the other two are significant. Okay, so here it is significant, and you see that here it is significant, except this. So in the adjustment coefficient, if one series adjustment coefficient is insignificant everywhere, then that indicate that is the original series. Okay, all the other two series are derived from that. Okay, and also it tells you about the causality. Okay, so here what happens is that X is causing Y and Z, not the other way around. Okay, so the key points we have to keep in mind is that if there are three variables and two co-integrating vectors, obviously that's the maximum we can get. If we get three co-integrating vector, then then there is a serious problem in the data. Most probably the variables are stationary process. Okay, so if you get three variables and three co-integrating relationship, it indicates that all the variables are stationary. So if it is 3, then the maximum co-integrating vector might be 2. If then it indicates that only one is creating the other. Okay, so if you are not, if you create this from another cumulative sum, okay, then you will get only one co-integrating vector. Okay, so the adjustment parameter will tell you to identify or indicate to identify the base series, okay, on which the other two series are derived. Okay. So even if you put the money, price and income in this system, if money is having an insignificant adjustment parameter, indicates that money is causing the other two, not the other way around. Okay, so it is as simple as this to interpret. Okay, so I'll stop here. If you have any questions, I'll be more happy to answer.
So there is already a question is posted, sir.
Okay, I'll go through it. Okay. Series having high correlation will also be co-integrated. Yeah, obviously, a random walk process, if they are having two highly correlated series, then there is a possibility of co-integration. But the problem is that the whole idea of spurious regression comes is that we it might be due to some other factors also. Okay, but in a simpler view, yes, if it is having high correlation, then it is co-integrated. But we need to test and see that. As I told you, the idea of co-integration is to identify which is the original process, so that we can infer something about the causality. Okay, so any other questions?
Participants, any questions?
Or is it too much? No, this is the basic, underpinnings of integration. If you understand this, then you can build on this.
So there are one more question, sir.
One more question, okay. So we have different nature of variables such as qualitative. How can we test qualitative variables? We can't test co-integration.
Yes.
It's as simple as that. Okay. So co-integration is a time series technique. It's not a cross-section technique. So qualitative variables mostly happens in cross-section. Say in time series, the qualitative variable comes in identifying some dummy variables to denote a crisis period or something like that. But how this is again, it's a qualitative variable. You can't do a co-integration test with that. The pi matrix will not come. It will become 0. There is a qualitative variable. Some light on dummy variable. Okay. So dummy variable in time series, or how it different from panel data analysis? See, I told you yesterday also, cross-section, time series, and panel data are 3 different types of data sets. And econometrics is totally different for these 3 different types of data sets. Okay, it is not same. As I told you, in cross-section, we are least bothered about the data generating process. Okay, there is no data generating process in cross-section data. It's all about samples, population, and all those. Okay. So time series has this data generation process. So panel data will have mixed both the characteristics of cross-section and time series. So there, again, we have the panel unit to test the stationarity of the time dimension in that panel data. Okay. So dummy variable, dummy variable itself needs a different session to.
Yes, sir. We have a session on that, sir.
Yeah.
Actually, qualitative response model, we have a session on that.
So dummy variable again, I'll tell you if it happens to be in independent variable, then the econometrics is different. If it happens to be in the dependent side, the econometrics is different. Okay, so that we have to keep in mind. So dummy variable has a lot of usage. It gives many real world applications. But as Dr. Balaji has mentioned, you have a different session on this qualitative dependent variable models.
Any more questions?
In the case of independent variable, yeah, dummy variable. Okay, so see again, there are multiple cases. If the dummy variable is coming alone or coming with another quantitative variable, so the interpretation, see the estimation remains same. Okay, so what you use in ordinary least square method, the same estimation or maximum likelihood method, whatever method you use, the estimation remains same if it comes as an independent variable, but the interpretation changes if it is coming independently. Only dummy variables are on the right hand side and no other quantitative variables on the right hand side, and it comes with a combination of these quantitative variables also. And if it comes with an interaction term, the multiplication of dummy variable and the quantitative variable, then see all there are 3-4 classification of this in that things. As I told you, it requires a different session to discuss. But it is of much use in real world application. Yes. And also, I think this year Nobel Prize has been given for that. So if you even though it's of a different kind, but we can boil it down to a difference in difference model for which this year Nobel Prize has been given in economic sciences. Okay, so dummy variables are very useful in identifying this difference in difference models. Okay.
There are no more questions.
Is use the only software to perform? No, there are any software can do it or can do it. There is a software called RATS, regression analysis of time series. Okay, so that can also do it, and Stata can do it.
Yesterday we had a discussion on this, sir. Actually,
So every software can do it, but for panel data cross section, see every software can do the analysis considering it as a cross section data. Okay. If you want to consider, if you want to tell the software that it is a time series, you have to define it first and then run the same thing. Then it will do the time series, as well as you have to inform the software that it's a panel data. So everywhere, we have to first define what kind of data it is, and then try to implement the model we want to implement. But in EViews and RADs, it's prevalently used. A lot of time series techniques are there and already inbuilt in the software. So there are, but every software has its own advantage and disadvantage. Which is the best method of co-integration? I think the best method is both the methods. Okay. So if you get some confusion in Engel-Granger, then you implement this. See, the best method is both the method. Both the method will tell you the same story. Okay, so both the methods concretely telling you that there is a co-integration, then you can 100% sure that there is a co-integration. If one method tells a different story and the other method tells a different story, then I think the data required some refinement. Okay. So Jorgensen is widely used if you have more than 3-4 variables. So there it is much better if you have a system of variables rather than 1 or 2 variables. See, if it is only 2 variables, both these will give you the same results.
okay, sir. I think there is no more questions. Induja, over to you. Induja?
I would like to take this opportunity to thank Professor Sethu Dure, sir, for this delightfully intuitive session, which, as a continuation of yesterday's session, was even more comprehensive and useful. This session was especially lively as something as fundamental as matrices and eigenvalues to the applicability, practical applicability of the model were made dynamic. So thank you, sir. With this, we will be concluding this session. The next session will be at 2:30.
Okay, thank you so much, Induja and Dr. Balaji, for this opportunity. Okay, so I hope people might have learned something out of this. Okay, I'll be more happy.
Thank you, sir. Thanks for accepting our invitation and for your time, sir. Thank you so much.
Thank you.
So participants, please join at 2:30. Actually, most of the participants left already. Good afternoon, Rafi. Dr. Rafi, how are you? After a long time? You unmute yourself, man.
Can you hear me now?
Yes, yes, Rafi.
Hi, Dr. Balaji. How are you?
Fine, man. Our HOD is here. Hello, sir. Rajagopal, sir. Good afternoon, sir. Okay, Rafi, you will wait for some time. People
Yeah.
have to join. Okay.
Yeah, fine.
Just 5 to 10 minutes.
Yeah.
Then you can, yes. I think we can start now. Induja, are you here?
Yes, sir.
Rafi will start. Dr. Rafi?
Yeah.
Yeah, we carry on. Yes, we can start now.
A very good afternoon and welcome to the third day of the online FDP on data analysis using econometric models. I would like to welcome our speaker for today, Dr. Mohammad Rafi Sir, Assistant Professor at Dr. B.R. Ambedkar School of Economics, University, Bengaluru. Previously, Sir has worked as a guest lecturer at Kannur University from 2012 to 2014. Sir has a PhD in economics from Pondicherry University in the area Open Economy Macroeconomics, an MPhil in economics from Pondicherry University, and an MA in applied economics. His areas of interest are in international finance, macroeconomics, and applied econometrics. Now, I would like to invite Sir to start our session today on panel data models.
Thank you, ma'am, for your introduction. Good afternoon, all of you. As you know, I'll be discussing about the panel data model. It's basically an introduction to the panel data and panel data models. And hope you have studied different time series models as well. So all those models can be applied in the context of panel data, which are we call it as the advanced econometric the panel data model. What we are going to discuss is when you want to find the relationship between two variables, we go for the regression model where we are basically checking the variation in the dependent variable which is happening, as a result of the variation in the input. So if, say, the independent variable increases by 1 unit, how much will be the increase or decrease in the dependent variable? That's what we are, we check using the regression model. And the widely used method is the ordinary least squares method. So what we are going to discuss, this OLS you can apply in case of cross-section data or in case of a time series data. Now we are going to discuss when we have a panel data. Then what are the advantages of using this data? Because our purpose is basically, to infer something about the relationship between these two variables. Now, usually we do not have the complete population in our hand. What we have is a sample, right? That sample can be either from, different individual units. We call it as a cross-section data, or that can be from a particular individual unit for different time periods. We call it as a time series data. Now, we are going to discuss when we have, both the elements. We have the time series element and the cross-section element. How do we model it? So this is equivalent to the, the ordinary least squares method, which we are applying in case of a time series data or in case of a cross-section data. Now, let me, begin with a brief introduction about the, the panel data, and we will also discuss about the, different advantages of using the panel data, and we will discuss the different models which we apply when we have a, panel data. I hope you can see the screen now.
Yes, sir.
All right. Okay. So, what do you mean by a panel data? The panel data is a combination of both the cross-section and time series data. So, the cross-section, we call a data set as a cross-section. Say, we are interested to find the relationship between, say, and say, we are going for the estimation of the absolute income hypothesis, suppose. We are checking when income increases, how much will be the increase in consumption. So the theory says that it is between 0 and 1, right? So we are actually checking how much is the value of the marginal propensity to consume, or the additional consumption generated as a result of additional rise in income. Now, this issue you can study. Say, if you are finding the, the microeconomic data, you can, you can look at the family income and consumption, or individual income and consumption from different families. Say you are collecting data from, say, 50 families on income and consumption. So you have two variables now, the consumption and income. So this is a cross-section data. So you have data from different individual entities, but for a particular point of time. So you are collecting, say, today, or you are collecting 2020. So this is for a particular time, but for different individual units. Or you can study this by considering the, the consumption and income of a particular family for different time period. Say if you're collecting data from, say, 1960 to 2020. So you have data, for this period. So you have data for different time period for a particular entity, right? You are collecting for a particular individual or a particular family. Or suppose you are talking in terms of, macro analysis, where you are looking at the private consumption expenditure and the national income of a country. Okay, now you are collecting data, say, from 1960 to 2020 for India. So this is a time series data. You have data for a different time period, but that is for a particular entity. Now, when you are combining these two elements, the cross-section element and time series element, So you are actually collecting data from different individual units for different time periods. Say you are collecting data from say 100 countries for 50 years. So this is a panel data where there is a cross-section element, number of cross-section is 100 and the number of time period is 50. So you are actually including both the time element as well as the cross-section element. In such case, you call it as a panel data. Now, when you discuss about panel data, often people get confused with the pooled cross-section data and panel data. So, what is the difference? See, when you talk about a panel data, you are actually following the same cross-section unit over a period of time. That means you are collecting data from the same individual unit for different time periods. But now you consider there is a survey. Say this survey is collecting data from 5,000 individuals in an year. Okay, so every year they conduct a survey. So suppose they are collecting data from Tamil Nadu from 500 individuals. Now this survey is conducted every year, but these respondents are being picked randomly. Therefore, the 500 samples from which the data is being collected this year might be different from the sample from which the data is collected in the last year or last to last year. And some of the respondents might be same, but the whole sample, if you consider, the sample might be different. So you are not following the same individual unit for different time periods. But whereas you have data on the individual units for different time periods, but these individual units are different. In such case, you call it as a pooled cross-section data or independent pooled cross-section data. They are independent. They are, the individual units are different. So often, we get confused with the panel data and the pooled cross-section data. So we are going to discuss about the panel data where we have the information about different individuals and we have information about these different individuals for different time periods. I hope you have a clarity on what panel data means. So we are why do we use the panel data, or what are the advantages of using the panel data than you going for a time series data or a cross section data? See, nowadays you can see that there are most of the research people take the panel data. So that's because there are different advantages. See, even from the publication point of view, if you take the publishers often consider a good data set where you have the representation from different cross section units as well as from different time periods. Now you consider the same example where we are studying about the consumption and income. Now if you are studying on a macro level where you are collecting the GDP data as well as the private consumption expenditure data, say from of 100 countries. Now you have data for 2021. So for this particular year, you are understanding the relationship between the consumption and income. The data which is being collected from different countries. Now you are saying that you are looking basically at when the GDP of a country is lower, but how much is the consumption, and when and you are looking at those countries where when the GDP is higher, what is how much is the consumption, and you are comparing this and finding the marginal propensity to consume or autonomous. So the sample is 100. Now See, our basic purpose now, we are going to say that when income increases by this much, the consumption is going to increase by this much, or the marginal propensity to consume is 7. I mean 0.7 or 0.6. That is the conclusion we are making. So from this sample, we are generalizing. Any econometric technique you take, we are actually generalizing about the whole population from a particular sample. Now, you have information only about 2021, and which is coming from different individual units. But now suppose you are, studying from a time series data. So you have data from India, say you have data from 51 to 2020. So you have data for 70 years.
Rafi, I think your slide is not moving. Dr. Rafi?
Yeah, can you see these advantages of panel
Yes,
data?
only
as
that
the
is what that. Yeah, now it's okay.
Yeah, okay, fine. Okay, so what I'm saying is, when you are having, say, when you are collecting time series data, say you have collected from India for say 70 years. So now you are talking about only the the relationship, which is about the income and consumption in India, which is for different time periods. So the sample size here is 70, and when you have used the cross section, it is 100. Now, suppose the same study you are conducting using these 100 countries for 70 years. Okay. Now, the sample you have is 7,000, right? The observation you have is 7,000. And ultimately, we are going to talk about the population from this sample. So, when you have a large, panel data, you are having a scope to have a larger sample size. So, when you have a larger sample size, these parameters which you are estimating from this sample will be more stronger. Or you can say that this will be more closer to the population parameters, right? So that is the whole purpose. So it is better to have larger sample, and the parameters which we are estimating, see, with confidence we can say that which represent the population parameter. So that is one advantage, and that is the reason why when we study about one country, or when we study about using a cross section, people say that they talk about how strong your sample is. So when you consider a panel data, you are making a a strong data set and a strong parameters. Secondly, when you have data from different individual units, definitely you get more variability in the series. Basically, we are trying to understand the variability in the dependent variable. Can that be explained by the variability in the independent variable? So we can have more variability in that, in any series, in say in consumption series or in GDP, because when you compare the GDP of two countries, you can see that there's huge difference, right? So when you include the heterogeneous group, say you are including the developing countries, or the developed countries, or some of the African countries, so what happens is that you can have more variability within the data, so you can capture the different dynamics there. And the you can have less collinearity among the variables. Say if you are considering the the wealth and the income as the independent variables. Now when you have data from say 100 countries, so the wealth of one country will not be affected, or will not affect the income of other countries, right? So the collinearity between these two variables. Otherwise, when you deal with the time series data, one of the major problem is that the variables will be collinear, or there can be multi-collinearity. The independent variables are highly correlated, so that can be avoided when or that can be avoided to an extent when you deal with the panel data. Now, another advantage is that you can capture the inter-individual differences and intra-individual differences. Okay, see, let me explain this benefit with an example. You are studying about the relationship between, say, oil price and stock price. So you have collected, say, time series data from India and found that when the oil price, the crude oil price increases, the stock price is coming down. Okay, so you are basically looking at what is happening or the variation within this individual unit over years. Now, suppose you are doing the same study using the data from UAE. Now, you may find that when the oil price increases, the stock price is also increasing. So, say if you are only taking data from India, you are finding a negative relationship, and when you consider UAE, you are finding a positive relationship. So, suppose we are going for a time series data analysis, where you are considering only one of the country, and the inference which you are going to estimate it's completely depends upon that particular data set. And two individuals, say one is coming up with the analysis from India and the other one from UAE, you can get two different results. So this might be because this might be, so you can say that there is a intra-individual, inter-individual differences. There is differences within, these two individual units, right? The relationship between the oil price and stock price, this relationship is different, within these two individual units. So there is an inter-individual difference. But when you consider a time series data, you are considering only intra-individual difference. That means the variation happening within that individual unit. So now, if you are collecting, say, two panel, so this might be because this difference might be because India is an oil importing country, whereas UAE is an oil exporting country. So what happens is when the oil price increases, the wealth of the individuals is increasing in UAE, which can push the stock prices up. But in case of India, you can see the opposite impact. Now, if you want to capture this intra-individual difference and inter-individual differences, say if you are comparing some of the oil exporting countries and another panel with oil importing countries, there you can capture both the what the variation happening within a country and the variations happening between countries. So this is another advantage of using panel data. You can capture the inter-individual differences as well as the intra-individual differences. And the one of the other advantage is that when you talk about an economic state of an economy, it is better to go for a panel data. Say, suppose you are interested to check whether a particular economic policy could bring some individuals out of poverty. Okay, so usually, either you can go for a cross section. If you are going for a cross section, above poverty. Now, if you have data 1,000 families or 1,000 individuals, if you are having data for this 1,000 individuals for two time periods or more than two time periods, so now you can see that how many individuals have come out of poverty or how many individuals are being pushed into poverty out of this 1,000 sample, because you have data for two time periods. So you can understand the economic state of a community or of a particular individual, then it is better to go for a panel data where you can capture the situation of a different individuals for different time period, which will enable you to understand how the situation of a particular unit is being changed. Or you are studying about the you are studying about the unemployment. Now, if you have data on the individuals where he is employed or unemployed, so if you have data for different years for a particular individual, you can better understand whether an individual is frictionally unemployed or there is a long-term unemployment in the economy. So this you can understand only when you have data for different time periods for the same entity. Otherwise, you just look at the unemployment rate in a country for different years. You don't know whether a particular individual, see if an individual, is being, pushed out of employment, but another individual, got employment in that context. But when you look at the unemployment rate, what happens is you have, the unemployment rate remains same. So when you have data on a particular individual for different time periods, you can understand the economic state of that that community. Now you can also capture or you can also consider the unobserved behavior of these individual units. Suppose you are studying the productivity of agricultural laborers. So there will be, some laborers whose productivity is higher than the other employees because of their natural ability or their work ethics. So which is unobserved. So when you look at the productivity of these different individual units, which is different, that might be because of some unobservable factors, or you can say that there is heterogeneity. So when you compare these, these employees, you can say that there is heterogeneity because the productivity is different for different individual units. So you can say that there is a cross-section effect, or there is an individual effect. So this work ethics or this natural ability is same for a particular individual for different years. But when for a particular year, when you compare between two employees, you can see that it is different. So there is a heterogeneity or unobserved behavior of individual units, which you can capture. Similarly, say, you are looking at this agricultural productivity. Suppose you are having a data for different years. And now you when the fertility of the land can change. Say suppose you are using the fertilizers, the fertilizer, the yeah, or extra. So what happens can deteriorate the the fertility of the land. Now, if you are capturing this, you can say that each year there is an effect, which you can call it as a time effect. So each year something is happening, whether it affects all the individuals' productivity, right? It affects all the individuals' productivity. So there is a time effect as well. There is a time effect as well. So what I'm trying to say is that you can capture if you are including different individuals and for different years or for different time period, you can capture the heterogeneity among the individuals, or you can also capture the heterogeneity happening between years. Okay, so these things you cannot capture using the the cross section data or time series data. So this is why there is a rampant use of the panel data, and you can see the different models have been developed to address the different issues in the panel data. Now, when I'll discuss about different models of panel data analysis. Before that, when you get a data, I mean a panel data. So these panel data are of different types. So how do you understand, or or you can say that, some of the techniques, they say that this technique is applicable to short panels or long panels or unbalanced panel or balanced panel. So you need to understand the different types of panel data. So based upon the type of the data or the way in which this data is being presented, because some softwares would need you to present the panel data in a particular way. So depending upon how do you present the data or the availability of the data, the panel data can be classified into different types. Say you can classify this into balanced panel and unbalanced panel. Say you have data for each cross-section unit for the same number of years. Say you have data for 10 cross-section unit for 20 years. Okay, so for all the cross-section unit, you have data for 20 years. Then it is a balanced panel. Say suppose you have 10 cross-section unit and you have data for 10 cross-section unit. Out of this 10, you have data for 5 cross-section unit for 20 years, and other 5 cross-section you have data for say 15 years. Then it is, you call it as a balanced panel. So the number of time series observation differs between cross-section unit in case of an unbalanced panel. Say, some of the technique when you read, you can say, those techniques are applicable only in case of, balanced panel. So you need to, understand the clear distinction between the balanced panel and unbalanced. I hope you are able to see the slide, right?
Yes, please go
Yes,
ahead.
sir.
Please go ahead, sir.
Yes, sir.
Okay, okay, okay. So, this is based upon the availability of data. And again, based upon the availability of data, you can, these two data set you can see. Say the first one is the balanced panel and the second one is the unbalanced panel, where in the balanced panel, we have data for 5 years for 3 individual units, 3 countries. And in this unbalanced, you can see that, the data is available for 5 years for India, 3 years for Malaysia, and 4 years for Mexico. So the availability in terms of, time, it is different. Then you call it as an unbalanced. So based upon the availability of the data, you can also classify the data into micro panels and macro panels. See, when you have, many cross-sectional units and a few time series, say suppose you have data for 100, countries for 5 years. So this is an example of micro panel, and this is also known as short panel, because, some of the techniques are applicable for micro panel, and or when you have macro panels, you can apply some panel data techniques. Therefore you understand the difference, that when you have high a good number of cross section data but a few time series data, then you call it as a short panel. And sometimes even some authors also explain in this way, when the number of cross section is higher than the number of time points, you call it as a short panel. But the basic idea is, you have many cross sectional unit and but a few or times. And the opposite of it is called a macro panel or long panel. Say you have data for many time periods. Say you have data for 100 years, but this data is available for say 5 individual units. Say then it is a macro panel. So in economics, you can see many of the macro panels, like when you are studying about the money supply, you can see that you get data for, or you are studying something about the the Indian states. And if you have data, say for from 1950 to 2020, from 20 Indian states, then you have more time period but a few cross-sectional unit, right? So this is a macro panel. And in case of a micro panel, you can give an example, like when you study about different firms. Say you are, talking about, some issues. Say you are talking about the dividends and the stock price of different companies. Then say you have data for, I mean the firms, you will have a micro pan. Okay. So, and but when you have a large, cross section and large time element, then you call it a mixed panel. It is based as wide panel or as a long panel. Okay, by wide panel, I mean, say you take an example where you have data for 5 years for 3 countries. The cross section is 3. So you are putting the data for each cross section unit in columns. And the data about a variable is presented in separate columns for different cross section unit. Then it is a wide panel. And when you are presenting, when you are stacking the observation, say here you can see that for India, we have data from 2013 to 2000. As I know, then next we are putting for this.
Dr. Rafi, your voice is breaking. There's some disturbance in the audio. Dr. Rafi?
Can you hear me?
Yes, it's clear, Rafi.
Okay, okay. Okay. So this thing is the long
Rafi, I think there is some break in the voice.
panel where we are stacking
Rafi?
Is it better now?
Yeah, it's better now, but it seems that keep on breaking up.
Okay. Okay. So any I can switch to other. Connection if needed. Okay, so different types of data. It depends where the advantages of the panel data model we have discussed. So you can have a larger sample size, and more than that, you can capture the heterogeneity.
Dr. Rafi, you're facing the same problem again. Rafi? I think he lost the connection. Just wait for a moment. Rafi?
Yeah, can you hear me now?
Yeah, we are hearing, but I think it's keep on breaking up. That's an issue.
Okay, just a minute, just a minute.
Yes, Mr. Ganesh is working on it. Just give him some time.
Just a minute, give me a minute. Is it better now?
Yes, clear.
Okay, fine.
Participants, is it clear? Fine.
So,
Yes, sir.
Yes, sir.
Yeah,
Yes, sir.
It is clear now.
all right.
yes, please.
I hope you can see the slide, right?
Yes, sir. We're able to see. Yes.
Yes, sir.
Okay, fine. Yeah. So, now when we have, panel data, what are the models available? You have, different models available, but equivalent to the ordinary least squares method, which we apply in case of a time series data or cross section data. You would have studied about, when you are having a time series data, you need to, look at certain issues. In the same way, when you have a panel data, you need to look at some issues. And there are different models available, such as the pooled cross section data analysis models, or the fixed effect models, or the random effect model. So let me discuss about the major distinction between these three. So when you have a panel data, you cannot choose one of these model and go ahead. So it completely depends upon the data, the characteristics of the data. So the data should tell you that this is the appropriate model you should go for. Then only you can infer and conclude about the relationship between, say, these two variables which you are talking about. Otherwise, what happens, say, if you are supposed to use a particular model, but instead you have used a different model, then you are concluding that this is the type of relationship exists. That might go wrong. So what we need to look at is, when we have a panel data, whether we are going for, or we are choosing the appropriate model or not. So how do you understand that? How do you understand that? Okay, and there are different tests available to choose between these models. So let me begin with the pooled OLS, or the constant coefficient model. So as the name indicates, you are pooling the cross sections, pooled OLS, or you are going for a constant coefficient model. So you are, not considering the variations, in this case. In that way you can read. So the pooled data and the pooled OLS is different. So the pooled data which we had discussed was, regarding the data set, but here we are talking about a regression where we are pooling different cross-section units. Okay, or different individual units. Now, say you take the same example where we have uh, say 100 countries data for some 50 years. Now, when you are going for a pooled OLS, what you are doing is you are pooling all the cross-section unit. You have 100 cross-sections, right? So you are pooling them together, considering that the behavior of these individual units or the relationship in all the cross-section units. So you are considering them as a homogeneous group in case of the pooled OLS. So what you do is you are pooling them together and assuming the homogeneity cross-section unit. So when you have a regression model, you have an interceptor or the constant you say, and the slope coefficient. Right? So these two, the intercept and the slope coefficient, does not vary across cross-section unit. So for all the cross-section unit, you are getting only one intercept and one slope coefficient. Basically, you are pooling all of them and considering as the same unit. So here you can see that yit is equal to alpha plus beta x it. So these I and t represent the cross section and time series respectively. So I means the individual units, the cross section unit, and t means the time series. So yit, see wherever you see something xit or yit, that means it's a panel data. You have both the data for different cross-section unit for different time periods. So here you look at the parameters alpha and beta. Say this is, suppose if y is consumption and x is the income, then alpha is the autonomous consumption and beta is the marginal propensity to consume. Now you are getting the autonomous consumption only one value for all the cross-section units or full sample. And the slope coefficient also you are getting only one value. Okay, now then the issue here is that there can be heterogeneity, right? There can be heterogeneity. That's the beauty of the panel data. There can be heterogeneity in heterogeneity between the cross-section units. Now, when you are pooling them, you are ignoring this heterogeneity or individual differences. You are actually, not including here. So that's a major problem, and then what you get with the inferences which you are getting might also be biased in the sense that you may not get when you are not capturing the differences within that sample, then whatever inferences you are going to say is actually not including these differences, and that might be wrong. So this is the major limitation of the the pooled cross section or sorry, the pooled OLS or the constant coefficient model. Now the beauty of the panel data is there is heterogeneity. So you should include this heterogeneity in the model. So how do you include this? That's a question. So let me give you an example where you can easily understand this heterogeneity. Say you are studying about the relationship between the education, the level of education of individuals, and the wage rate. Okay, so you have data, it's a panel data in the sense that, suppose you have data from both male and female. Okay, so let me consider this as two cross-section units, the male and female as two cross-section units. Now, in a pooled cross-section, this is the way you are defining it. But now, suppose you are separating male and female samples. and finding the relationship between education and wage rate. Suppose you get something like this. When you have the years of education on the horizontal axis and the wage rate on the vertical axis. Now you have two regression lines, one for male and one for female. Right? So these are the samples. Now you can see that, you can clearly see that if you compare the male and female with the same level of education, the wage rate for the male is higher than the female always. But the slope of this, two lines, two regression lines are same. That means when the education is being increased by 1 year for male or for female, the change in the wage rate will be same. So the slope is same, but whereas you can see that the intercept is different. The intercept is different. Now, when you are pooling this, you are not considering this difference. You are not considering the difference in the intercept when you are pooling these two cross section units. So that's a major problem. That means there is a heterogeneity. There is a heterogeneity between male and female. Now, you do not consider when you are pooling. See, when you are pooling, you are getting a different regression line. Only one regression line which you are getting, and you are concluding about the alpha and beta thing. So this is a major problem when you deal with the panel data with the the pooled OLS. Now, how do we consider or how do we deal with this heterogeneity? The heterogeneity, see here in this example, we are considering these two, for the illustration, we are considering male and female as two different groups or two cross-section units. Okay. Now, this is a, common case, right? The wage rate, is different for, with the same level of education, the wage rate can be different for, male and female. Now, how do you include this? Say, now there are different methods available to deal with the unobserved heterogeneity. I mean the heterogeneity between the cross-section units. Now, one of the method is the first difference method. So there is unobserved heterogeneity, which we did not mind when we have used the pooled OLS. Now, in the first difference method, we recognize that there is heterogeneity. So what we do is, say there is a difference between two individuals. Now, you consider that this difference, the difference in the wage rate or difference in the productivity is because, say, one individual is, he is, more ethical, or you can say that, these individuals, these two individuals, the productivity or wage rate is different because uh, there is a natural ability, there is a difference in the natural ability of these two individuals, or there is a difference in work ethics, suppose. Okay, so and this work ethics or the this is same for this individual for different years, right? It is not changing, or it is compared to last year or last to last year, it is not changing. So this is a particular character which is there for a particular individual unit. So this is different for two individual units, but for the same individual units for different time period, it is same. So now the first different method uses this, and what it does is when when you can write yit is equal to alpha plus beta 1 xit plus beta 2 wit. Say suppose y is consumption, x is income, and w is wealth. Okay, so we are going for a consumption function where we are including income and income and wealth as the independent variables. Now, if this is the type of relationship, then you can write yit minus 1. See, yit minus 1, I mean the last period consumption function. If today's consumption depends upon today's income and today's wealth, definitely last year's consumption depends upon last year's income and last year's wealth, right? Therefore, you can write it as yit minus 1 is equal to delta plus beta 1 xit minus 1 plus beta 2 wit minus 1 plus uit minus 1. See, uit or uit minus 1 is the error term. Okay. So now what first difference method does is you just see the difference between these two. Today's income and yesterday's income, or today's consumption and yesterday's consumption, or today's wealth and yesterday's wealth. Now, this is basically to deal with the heterogeneity between individual units. Say now the assumption here is this heterogeneity, this is different for different individual units, but it is same for an individual unit for all the years. That's a cross-section effect, right? That's a cross-section effect. So you can say that if you deduct today's income from yesterday's income, or today's wealth from yesterday's wealth, so these individual differences can be, you can remove this, because this, if something is special for an individual for this year and which is there in the last year also, so when you are deducting last year's, then you are actually removing, right? So you are removing these differences. You are removing these differences. So basically what you do is, instead of modeling yit, you are modeling delta yit. So delta yit as a function of gamma plus beta 1 delta xit plus delta uit. See here, say the wealth is same. Say we have data for 5 years and the wealth of these individuals are same for all the 5 years, suppose. So that is why, in the last equation, I have removed those portions. If wit and wit minus 1 are same. Okay, so if both of them are same, you remove that component. But if xit and xit minus 1 are different, then you get delta xit. But whereas you remove something, which is there for each individual unit, because you are deducting, from the last years. So you remove the, the heterogeneity. You remove the heterogeneity by taking the first difference method. By going for the first difference method, you remove the heterogeneity. So instead of modeling yit, you are modeling delta yit as a function of delta xit. So this is the first difference method, where this method consider the individual differences and try to remove the individual differences by taking the first difference. So this is one way the unobserved heterogeneity can be dealt. Another way is you can you can go for the within transformation, or what is known as time demeaning. Now, see, in the last case, in the first difference method, we have detected the last year's value from this year's value, assuming that the individual special character is same in the last year and this year. Now, in the time demeaning, what we do is we are going for a within transformation. So instead of taking the last year's value, we take the average value. Average value for each individual unit. Say suppose we have data for 10 individual units for say 50 years. So you take the average for the first individual unit for this first, for this 50 years. Similarly, you calculate the average for the second individual unit till 10th individual unit. Similarly, you do it for all the variables. Now, what you do is, instead of deducting the last year's value, you are deducting the average. Because if there is something special for an individual, when you take the average, that is definitely will be there, right? So when you remove, when you detect the actual value from its mean, you are actually removing these differences. So here you are deducting yi bar from yit and xi bar from xit and wi bar from wit. So suppose the wealth of the individual is same all the years, then WIT and WI bar is same, right? WI and WIT and WI bar is same. If wealth remains constant for all the years for a particular individual, then in that case, you can write it as YIT double dot is equal to beta 1 XIT double dot plus epsilon IT. Okay, epsilon IT is UIT minus UI bar. Okay, so this is another way. This is another way in which you can deal with the heterogeneity. Here again, you can see that what we do is we are removing the heterogeneity by taking by subtracting the average of each individual unit from the actual value or from the last the last period value. So this is two ways in which you can deal the heterogeneity. But whereas at least these two models, they consider the heterogeneity, or they consider that there is heterogeneity among the individual units. But again, these do not include the heterogeneity in the model. They do not include the heterogeneity in the model. Therefore, there is another model known as the fixed effect model or the least square dummy variable model. So this is an alternative model which try to include the heterogeneity among the individual units. Okay, so instead of pooling the individual units, or instead of removing the heterogeneity by taking the first difference or time d mean or within transformation, what the fixed effect model does is it tries to include the heterogeneity in the model. Now, so the difference between the pooled OLS and the fixed effect model is that the fixed effect model allows the intercept to vary across the cross-section unit. See, consider the earlier example of wage and education, where the intercept was different, right? When we had gone for a separate analysis of the relationship between the of the relationship between the education and wage rate, we have seen that the intercept is different for these two cross-section units. Now, the fixed effect model allows the intercept to vary across the cross-section unit. So now, when you have the wage rate, the relationship between the education and wage rate, we have written when we use the pooled OLS, the alpha and beta value, you get one alpha and one beta value for all the cross section unit. But in case of but the relationship it was that you have to see the slope is same here, but the the intercept is different. Now, how do you include that in the model? Say, now you can see that when you define wage IT is equal to alpha I plus beta education IT is equal to UIT. So here you can see that the intercept, you can see that it is written that alpha I. I means that you get intercept for each individual unit. Say if you have data from say in this example, if you take, you get the intercept for male and female separately. If you consider male as one individual unit and female as another individual unit, or say if you are having data for 10 cross section, then you get 10 intercept. You get 10 intercept. The intercept will be different for each individual unit. So that is how the individual difference is being included in the model. Now, say, here you get alpha 1 and alpha 2, or say alpha M and alpha F. This is the, the autonomous consumption. This is the alpha for male and alpha for female. You get two separate intercept, or you get two constants. Okay, so this is how the fixed effect model includes the differences, the individual differences. Now, a general form, you can write this as yit is equal to alpha I plus beta xit plus uit, where you can see that the intercept you get for each individual unit, but whereas slope, there is only one slope coefficient for all the individual unit. Okay, so that's a difference. That's a difference between the pooled cross section and the fixed effect model. Now, how do we get different intercept coefficient? Say when you estimate how we are able to get different intercept coefficients. So what you can do is you can introduce dummies. Okay, so in this example, you have the male and female. Now you can introduce two dummies, where you are introducing a dummy, let me call it as D1T. Okay, so D1T for the first cross section unit. So you are giving 1 for the first cross section unit and 0 for the second cross section unit for one dummy. And say in this case, for male you are giving 1 and for female you are giving 0. So D1 will take 1 for male and 0 for female, and another dummy you are introducing, D2T. D2T will be equal to 1 for female and will be equal to 0 for males. Okay, so you are introducing two dummies, and here you closely watch that we have not included another intercept, because we have included two dummies for two groups, right? We have two groups, we have included two dummies. So when you have studied about the dummy variable, you would have studied about the issue of dummy variable trap. Say if you have two categories, if you are including two dummies plus an intercept, this will create the dummy variable trap, right? So when you are introducing m number of dummies, or when you are including m number of cross section or m number of categories, you need to introduce m minus 1 number of dummies if you are including one intercept. Otherwise, you can include m number of dummies without introducing an intercept. So here, if you are defining it in this way, you should not include an intercept. Here, you are including two dummies for two categories. So alpha 1 will tell you about, it is basically alpha 1 is the intercept for male and alpha 2 is the intercept for females. So you get to intercept. You get to intercept. So suppose alpha 1 alpha 1 is equal to alpha 2. That means there is no individual difference, right? If alpha 1 is equal to alpha 2, then there is no individual difference, and this model will bring down to a pooled OLS if alpha 1 and alpha 2 are same. So if alpha 1 and alpha 2 are different, then there is a difference in the intercept. Therefore, this becomes a fixed effect model. So this way of defining the fixed effect model is known as the least square dummy variable model or the LSDV model, where you are introducing a dummy variable for each of the cross-section unit, which will serve which will give you an intercept for each individual unit. That is how you can capture the individual differences. So you go for a least square dummy variable model, which will tell you whether there is a difference in the intercept among the individual units. So here we have only two cross sections. So we have introduced two dummies, D1 and D2, and we got alpha 1 and alpha 2. So it all depends upon how many cross section units are there. Say if you are talking about, say if you have studying about the relationship between say two variables in case of 5 countries, then you have to introduce alpha 1, alpha 2 up to alpha 5 dummies. The first dummy for you are giving 1 for the first country and 0 for all the countries for D1. For D2, you are giving 0 for first country, then 1 for second country, and again 0 from third to fifth countries. So in that way, and you introduce D3, where you give 1 for third country and 0 for all other countries. So in this way, you introduce different dummies and include it. And the number of dummy should be equal to the number of the cross section, and you should not include any constant there. Okay, so this is how you can capture the individual differences, the differences in terms of the intercept you can capture. Now, how do we choose between a pooled OLS and a fixed effect model? How do you understand whether, as I said, either you should go for a pooled model or fixed effect model? You cannot choose one model and go ahead. So how do you know whether it is a fixed effect model or it is a pooled model? So what you do is you go for a fixed effect model. I mean the the LSDV model. Suppose you have n number of cross section unit, and here you are introducing n number of dummies from D1 to Dn. Plus you have the main independent variables, say education, and YIT is wage rate. So you have different categories. Okay, n can be anything. Say suppose you are there is a wage difference between the people living in different parts of the country. Say if you consider South India, North India, Northeast, and Northwest. Say if you are categorizing 4, then you have to introduce 4 dummies. So n becomes 4. So you introduce different dummies. So n number of dummies we are introducing and going for estimation. Now we get alpha 1, alpha, and we also get beta. So we are introducing this and got the result. Now, say if alpha 1, alpha 2 up to alpha n is equal to, or if they are same, then it is a pooled model, right? Then you don't have to introduce this many dummies. So you go for a fixed effect model or LSDV model and check whether these variables are same or not. So usually we go for the statistical significance, right? So in case of a single coefficient, we go for t-test. Or you look at the probability value corresponding to that t-test, right? You are checking whether that coefficient is equal to 0 or not. or if it is equal to 0 or greater than 0, you can go for one-tailed or two-tailed test, right? So if you are checking for a particular coefficient, you go for t-test. But if you are checking the overall significance, or you are checking a group of coefficients, then you go for the f-test, right? You go for the f-test. So similarly, we are here going for the restricted f-test. So what we do is we are collecting, the R square. So our purpose is to check whether alpha 1 up to alpha n is same or not. Okay. So the null hypothesis is the null hypothesis is that all these coefficients are same. Okay. Suppose if the null hypothesis is true, then it is a pooled OIS. But if you reject the null hypothesis, then it is a fixed effect model, right? If you reject the null hypothesis that the intercept of all the cross-section units are same, then it is pooled. If you reject that, then it is a fixed effect model. Now, basically what we do is we have the constant coefficient model and fixed effect model, right? We have the pooled model and fixed effect model. So in the pooled model, you have one intercept and one slope. But in the in fixed effect model, we have different intercept and one slope coefficient. Therefore, the R square will be different because these are two models. The dependent variable is same, whereas the independent variables are different, right? Therefore, if you have a model with the same dependent variable and different independent variables, you can compare it using the R square, right? Now, you are comparing it using the R square. So you are capturing the R square from the fixed effect model and the pooled effect model. And you are adjusting it for the degrees of freedom. Now, the R square you are coming from the fixed and the the pooled effect model or pooled model, and n is the number of intercepts or the number of cross section. Okay, so how many cross section units you have? Say n is in the male female example, n is 2. So we have alpha 1 and alpha 2 only. And nt is the total number of observations. Say if you have 50 years of data for 10 cross section unit, then you have 500 observations, right? You have 500 observations. So total nt is the total number of observations, and you are detecting n and k from the total observations. Number of explanatory, k is the number of explanatory variables. Okay. So t minus n minus k is nothing but the degrees of freedom. So you are adjusting it for the degrees of freedom. So in this way, you can calculate the F test. Now, when you calculate the F test, you have to compare it with the the critical F value, right? So if the actual F value is higher than the critical F value, then you reject the null hypothesis. So if F stat is significant, you reject the null hypothesis. The null hypothesis here is you can pool them together. So if the actual F is greater than the critical value, or if the actual F is significant, then you reject the null hypothesis and you go for the fixed effect model, because you cannot pool them together. You are out. Okay, so you can choose between the fixed effect model and the pooled effect model using the F test. Okay, now suppose you found that the pooled effect model is not appropriate, then you can go for the fixed effect model. Now, there is another model. Okay, before getting into that, the two limitations of the fixed effect model is when we include, see, the degrees of freedom is nt minus k minus n. Now, k is the number of parameters, right, or the number of the independent variables. So what happens is that as you increase the as you increase the observation, sorry, as you increase the the cross section unit, or if the cross section, or as you introduce the dummy variables. So what happens is that when you introduce dummy variable, k is going to increase. Therefore, the degrees of freedom will reduce when you go for the least, LSTV model. So it will affect the degrees of freedom. That's one of the limitation of the fixed effect model. Especially when you have 100 cross section unit, you have to introduce 100 dummies. So that is going to reduce your reduce the degrees of freedom drastically. And another issue is there can be a problem of multicollinearity. Say suppose you have 100 individual units. Now you take the case of first dummy where you are giving 1 for first cross section, I mean first individual unit, and 0 for all other. In the second dummy, you are giving 0 for first, then 1 for the second, and for rest 98 you are giving 0. So you can see that the value is same for most of the portions for dummy 1 and dummy 2, right? So this can lead to the multicollinearity problem. So this is another problem with the fixed effect model, but you need to understand one thing. Here we are including the differences, the individual differences in the model. Okay, and another alternative model is the random effect model. So the random effect model does not use the dummy variable to calculate the presence of individual effect. So instead, what it does is it assumes that the individual effect, see the alpha I which we are talking about. So this individual effect is a random variable with a mean value. Okay, so this individual effect is a random variable with a mean value, or that means that the intercept of ith cross section unit, you can write it as the alpha I, which you can write it as alpha 1 plus ei. Okay, see, this alpha I is the the individual effect, and which you can write as, see, you have a common effect, right? You have a common effect. So you can write it as alpha 1 plus ei. So the individual effect, you can write it as alpha 1 plus ei. So here, we are assuming that the cross-section unit in our data set have been, driven from a much larger population. Okay. And they have a common intercept. This intercept is alpha 1. So this individual difference is being considered purely as a random component. So this individual difference is being captured by this random error term, ei, right? Ei capture the individual difference. So thus the random effect, you can specify this random effect as if you can write alpha I is equal to alpha 1 plus ei, you can write yit is equal to alpha 1 plus ei plus beta xit plus uit. Here, alpha 1 is the the common intercept, and ei is the random component. So now, if you bring this out of the bracket, you can also write this as yit is equal to alpha 1 plus beta xit plus eit plus uit. So eit is a random component. And again, uit is the the error term, right? The error term, a combined time series and cross section random error component. Now, if you are, combining these two, you can write it as yit is equal to alpha 1 plus beta
घंटे से कर
x
2 घंटे से कर लो तो 2 बजे तुम्हें दे रखी थी मैंने चिमनी.
So yit you can write as alpha 1 plus beta xit plus
इसके
vit.
कटा दुआ कर लो जो 30 रुपए कटे मेरे मुंह से तुम लोग गाली जानबूझ के नहीं कटवाते हो. हाँ तो तुम कह रहे हो 300 रुपए.
Can all of you mute?
200 रुपए मेरे वहां कटे जब मैं तो नहीं गया ये हरिराम.
Can all of you mute, please?
आज के दिन हमारी बिल्ली खत्म हो गई थी. तो सुन लो.
Okay, thank you. So, you can write it as alpha 1 plus beta xit plus vit. So here vit is a composite random error term that has two components, eit and uit. Sorry, ei and uit. Okay, ei is the, ei is the individual specific random
मीटिंग से
error
बाहर हो गया. रिवीजन कर सकते हैं.
and uit is the combined time series and cross-section error component, random error component. Okay, now you can estimate, you can estimate this model, and where this random effect model assumes that the composite error term VIT is not correlated with any of the explanatory variables. So if VIT is correlated with the explanatory variable, then it creates a problem, right? It gives you inconsistent estimate. So one of the assumptions of the random effect model is VIT is not correlated with the explanatory variable. But if VIT is correlated with the explanatory variable, then it leads to the the inconsistent estimator. So what we need to look at is that when the composite error term, where this composite error term, this EI is a part of composite error term. If that is correlated with the explanatory variable, then which will give you inconsistent estimators. Okay, so we need to see whether we are getting a consistent estimator or inconsistent estimator. So so this is another alternative which you can make use when there is a individual effect.
Can you just repeat the last slide?
This one.
Yes, sir. Yes, sir. Thank you, sir.
Yeah. Okay. So here in the random effect model,
इसको अगर मैं कल सुनो सर, एक बार मैंने ये डाउनलोड तो कर लिया अटेंडेंस शीट और ये स्क्रीनशॉट. मैं नहीं ले लूं तो कैसा रहे इसको?
Will you be able to
In Dubey, can you please switch off your audio?
All the candidates? Will you be able to mute all the participants? As a host, I think you'll be able to do it.
शांत रहो सर, एकदम शांत रहो, एकदम शांत रहो. तेल देखो, तेल की दाल.
Raveen sir, please just mute yourself. Raveen Dubey sir, just mute yourself, please. Yes, sir, you may continue, sir.
Yeah, thank you. Okay, so in the random effect model, these individual differences are being treated as a random component. Okay, so see here you can see that the YIT you can write it as alpha 1 plus EI plus beta XIT plus UIT, where we are actually splitting the individual differences, or the individual differences, the alpha I we are considering as the difference between a common mean and the random component EI. Okay, so this random component, if you expand, you can write it as alpha 1 plus beta XIT plus EI plus UIT. Here EI is the the random component, particularly to, with respect to I error, the usual error. So if you are bringing them together, you can write a combined, or composite random error term, which is equal to VIT. Okay, so VIT include EI, that is an individual difference, that is a pure random component, plus the usual, the T is correlated with XIT, suppose. Okay, that means, or EI, the individual difference is correlated with the explanatory variable XI. Then VIT is correlated with XI. So what happens? See, you would have studied about one of the assumptions of binary least square method is that the error term and the explanatory variables are not correlated. They are not correlated. Okay. So, but when they are correlated, what happens is that you get an inconsistent estimator. You get an inconsistent estimator of the independent variable. So this is one of the major problem when you apply the random effect model. Okay, so I'll explain about how do we choose between the fixed effect and random effect. So suppose if there is an individual effect, we cannot go for pooled effect model, but pooled OLS, but you can go for a fixed effect model or random effect model. Now, how do you choose between these two? So, there is something called the Hostman test. The Hostman test will help you to choose between the random effect model and the fixed effect model. So here, the null hypothesis here is that the fixed effect model, both the fixed effect model, the beta Fe and beta Re means the parameter of the effect model and random effect model respectively. So the Hostman test assumes, the null hypothesis is that both are consistent, but the fixed effect model estimator is inefficient. Okay, or you can say that the random effect model is appropriate or better. Okay, so null hypothesis is that the random effect model is appropriate, and the alternative hypothesis is the fixed effect model is consistent and efficient. But whereas the random effect model, the parameter from random effect model is inconsistent. Okay, that means the fixed effect model is appropriate. That is the alternative hypothesis. So the null hypothesis is that the random effect model is appropriate, and the alternative hypothesis says the fixed effect model is appropriate. Now, this actually uses the chi-square. Okay, the Hostman test is using a chi-square distribution, and if the actual chi-square value is greater than the critical chi-square value, then you reject the null hypothesis. Here model is appropriate. So if you are rejecting the null hypothesis, then you will go for the fixed effect model, right? So you look at the chi-square value from the Hostman test, which will tell you the choice between the fixed effect model and the random effect model. Okay, so you can choose between the fixed effect model and random effect model using the Hostman test, and you can choose between the pooled OLS and fixed effect model using the F test, the rest. Now, I'll also take up a data set and show you how do we, estimate this. But before, getting into the estimation, let me discuss about the one-way and two-way fixed effect or random effect model. Okay. So far, we have discussed about the one-way effect model where we had considered only the differences between the individual units. So that this difference happens between two individual units, but this is same for all the time period. This is the same for all the time period. Then you call it as a one-way effect, where we are considering the that the intercept is different for different cross-section unit. So that's what we have discussed so far. Now, suppose there is then you write it as alpha I. Now suppose there are two effects: the cross-section effect and time effect. Say, when we had discussed about the agricultural productivity, say every year, suppose the quality of the land is reducing every year by something. Okay, so there is a time effect as well. There is a time effect as well. So every year something is happening, and this is common for all the cross-section units. All the cross-section units. Then this is including the period effect. Okay, so in the two-way effect, apart from the the cross-section effect, we are including the period effect as well. So when you can write this as yit is equal to alpha I plus lambda t plus beta xit plus uit. Here you can see that intercept, different intercept for different cross-section unit, and lambda each year. Say if you have 5 years, you get lambda 1 up to lambda 5. So every year something is happening. So that you are capturing using the time effect. Okay. So when or when you have a panel data effect, you must also look whether there is, you must look whether there is time effect or not. If there is time effect, you include another term, say as lambda t, which will be the impact which is happening every year or the time effect. Okay, so this is the either a model, the data set if you get it can be either a one-way effect or a two-way effect. Okay, so when you get a data set, you should also look at whether there is time effect or whether there is cross-section effect. So when you are getting a panel data set, what you need to look at, you need to look at whether it is a one-way effect or two-way effect. And you should also see, you can infer about this relationship either using pooled or fixed or random effect model. You cannot apply whatever you want, right? So you should ask the data which model is appropriate. And accordingly you choose, and then then you infer about the relationship between the independent variable and the dependent variable. Okay, so I'll take up a data set and show you how do we or the estimation using one of the software. I'll use the eView software, which helps us to estimate these different models. So now I have a data set. Say I have the growth rate of GDP per capita. So the per capita GDP growth rate and the trade openness. So these are the two variables I have, and I'm interested to see country is more open for trade, growth of the economy or not. Every unit dependent variable as y and variable as x. representing the openness, y is representing. And we have data from 9 7.
I think it is visible to us. Just a minute, Rafi. It's visible to us. I think problem may be your side. Friends, are you able to see the screen? Dr. Rafi, just a minute.
We're able to see the screen.
Yes, we are able to see it.
Then Rahul, I think it's your problem.
Okay, so I think maybe he can or she can rejoin. That will improve. So we have data from 1980 to 2017. So this is annual data for different countries. So I have data for 5 countries. Okay. So the last column is the cross section ID. So I have data from 5 countries for the GDP, the growth rate of GDP per capita and trade openness. And I have data from 1980 to 2017. Okay. So let me copy this. Let me copy this data or what we are interested is X and Y. Okay. So let me copy this data set and let me open the video where I this would not be the first class on reviews, right? You had some reviews. Okay, so let me open a work file. Let me open a work file where you find either a cross-section data or time series data or a panel data, right? So what we have is panel data. So let me choose the balanced panel. Okay, where you can choose the frequency, and what I have is the annual data from 1980 to 2017. And we have data from 5 cross sections. Okay, so I'm defining the data set. Then I can import the data set here. I can bring the data set. So what I'm doing here is I'm defining the data set, which is from 1980 to 2017 and for 5 cross section units. Here you can see that the data is for 190. There are 190 observations. So let me go to Quick and empty group where I can copy paste the data. So here let me paste the data. Y is the dependent variable and X is the independent variable. Okay. So here you can see that this is in a long format, right? This is in a long format where you are stacking the data of all the individual units in a column. So we have 2 columns, one for the dependent variable and one for independent variable. So, the long format panel is what the, panel data. Okay. So what we are interested, here is to see how the growth rate respond to the changes in the trade openness. So Y is the dependent variable and X is the independent variable. So as usual, you can go to Quick, estimate equation, and you can type the dependent variable and the constant and independent variable. Okay, and you can go for the the model. So by default, EViews will go for the pooled OLS. Okay, EViews will go for the pooled OLS. Now, if you want to change this into a fixed effect model, see there is an option called panel options. And here you can change. See here there is cross-section effect and period effect. Okay, so here you need to change. So if this is a one-way effect, only there is cross-section effect, then you can change here. But if there is period effect as well, you can change here. Now, we do not know whether you have to go for a one-way model or two-way model. You do not know, or you have to pool it. Okay, so what you do is if you select none, it is a pooled model. So initially you go with pooled OLS. Okay, this is the result from pooled OLS, and you can see this right now. You do not know whether this is a fixed effect or random effect model, or you do not know whether it's a one-way or two-way model. So first, before getting into fixed effect and random effect, what you can do is you can check whether this is a one-way effect or two-way effect. So you can, from this window, see, first you have to go for pooled OLS, then you go for, from this estimation window, you go to view. From view, there is fixed effect or random effect testing. Okay. Basically, we are checking whether there is, one-way effect or two-way effect. And there is omitted random effect. Lagrange multiplier test. This will give you an idea about whether we should go for a one-way effect or two-way effect. So from the pooled OLS, you go to view, fixed effect or random effect testing, and omitted random effects. Okay. Now this is the output where you look at the Brosh-Pagan test, which will tell you about the cross section and time effect. Okay, so there are numbers in three columns. In the first column, it talks about cross section effect, and the second column talks about the time effect. Okay, so you look at the there are different tests available. You look at the first test, which will give you an idea about both cross section and time effect. So you look at these numbers. Okay, and what is the null hypothesis here? There is no effect. This assumes
Rafi, we lost your connection, I think. Rafi, we're not able to hear you, man.
He's not audible.
Yeah, maybe.
He lost his connection.
Connection, yes, ma'am.
Yeah, he
Yes,
lost
yes.
his. Yeah.
Rafi, yeah, just wait for a minute. Let him connect. The participants, actually, if you have any doubts, except panel data, because I'm not masters in panel, maybe in time series or anything on that, we may have a small discussion, because before going to your exams, if you want to get clarify anything, you can ask me, except panel. Even panel, somehow I can help, but not like a specialist thing. So probably after this session, we can have some 10 minutes. If somebody have any questions, you can post it on time series and the data and other things. Am I audible for all?
Yes, sir. Balaji, sir.
Yes,
Sir,
yes, ma'am.
Yeah. Sir, we are finance people. We are listening this all those things first time. So for us, it is. I'm since morning. I'm actually noting each and everything, and I'm checking it also, because we are not from the econometric side, no.
Ma'am, actually, tomorrow is your thing,
Yeah.
ma'am. What you're going to
Yeah.
use generally.
Yes, we.
Arch catch models, actually.
Yes, only Ashkash model only. And but it's very interesting. He is teaching so patiently now, so I have noted each and everything. I missed only one slide. Besides that, everything I could note down. So
Right, ma'am.
very. There are two faculties who are taught very patiently. This I could figure it out, but besides that, it is very difficult. Hopefully, after this, FDP, I will connect with you to learn
sure,
it
ma'am.
properly.
It's my pleasure.
Yeah. Yes, sir.
At least I'm happy. At least very few participants take something from here,
Yeah,
because
sure.
only half of the people are here. Almost 200 who got registered. Only 120 is frequently attending. So anyhow, at least 10 or 20 will take something. I'm happy.
I also agree with ma'am, because today's session was very much informative and like interesting. I'm also like learning it. So I was not questioning much, because I'm also learning it from the like for the first time, you can say. I am from economics, but I have not learned these things before. So it was actually very informative for me also. I'm also noting every point as ma'am is saying.
Oh,
So
fantastic.
thank you, sir.
Yeah, good.
Sir, I have
Sir,
taken all
Thank you
screenshots.
so much.
So maximum screenshots I have for the
Don't worry, ma'am.
PPT. Yes.
We'll share the
Yeah.
PPTs.
No,
Actually,
no.
the problem is what
Uh,
happened is this resource person is supposed to share other documents also. They have to share their questions. They have to share the TLE
yes.
forms. So they took some time. So we are not able to push them. That's the problem. These people
So,
are very
Bala
busy.
sir,
Yes.
humble request, na, keep your question papers easy for people like us.
Ma'am, to be
Because
very honest,
otherwise it
even I
will
don't know
be,
what type of questions they are going to ask. Okay, it's MCQs only. That only I can suggest
yeah,
you.
because
Okay.
see, I'm not bothered about the certification. I just joined because of the I was very interested in learning the econometrics for so many years because I tried it. So that's what.
I
Otherwise,
think
it's very
resource
really
person join,
interesting.
ma'am. Let
Yeah,
him finish. We
sure.
can talk.
Yes, sir.
Rafi,
Yeah,
are
yeah.
you okay now?
Yes,
Yeah.
I too
Okay.
agree with
You know,
Nirmala
yeah.
ma'am because I'm also from mathematics background
Okay.
and many of the concepts are new to me also. Same is the mine case also, like Nirmala Joshi ma'am.
Okay, man. Okay. Rafi, are you available?
Yeah.
Yeah,
Yeah. Fine.
if you're clear,
Okay.
you can
So
carry on now.
I'll take another. Yeah, I'll take another. Yeah, I'll take another 5 minutes and
Yeah,
wind up.
please.
So yeah. So we are we found that okay. And now let us see. We go for the fixed effect and we can go for the F test and see whether should we go for the fixed effect model or not. So you can change the there is only one effect, cross section effect. You change into fixed effect model and estimate it because there is no period effect. So you change this into. I hope you can see the video, right? You can see what I'm doing here, right? Okay, so now let me go for the fixed effect model, and here you can see that the result. Here you can see the result, but we do not know whether this is a fixed effect model or we should go for the pooled effect model. Therefore, after doing the fixed effect model, see, once we have done the fixed effect model, then you can check whether we should really go for the fixed effect model, so that you can go to view. You can go to view for that and fixed effect random effect testing, where there is redundant fixed effect. We are checking whether we should go for the the fixed effect. So this is the the F test I was telling. So here you can see the F test result and probability value. Okay. So the probability value tells that you can reject the null hypothesis. The null hypothesis, remember well, which tells that you can pool them together, right? All the alphas are equal to or all the alphas are equal. So you reject that. This is not a pooled model. This is not a pooled model. You can go for the fixed effect model. Now, you cannot go for the pooled model. Rather, you can go for a fixed model or random effect model. Now, let us go for the random effect model. Random effect model. And okay, so this is the result from random effect model. See, you can notice the change in the the coefficient. So let me okay. You can say let me go for this is the result from random effect model that I have freezed. Okay, fine. Anyway, I'll come to that. So here we have gone for random effect model. We have gone to estimate and panel specification. We have chosen the cross section as random. Now you can choose between the fixed random effect model using the Hostman test. You go to view again, fixed effect random effect testing and the Hostman test, the last option, where you can see the the chi-square test which we were talking about, right? You look at the probability value. The probability value says that you have to reject the null hypothesis. And the null hypothesis in Hostman test is that the effect model is appropriate, or the fixed effect model is inefficient, but random effect model appropriate. So here the probability value says that you have to reject the number. That means the random effect model is enough. Model which we should go for is the random effect, the fixed effect model, not the random effect model or size of the trade, the export plus import divided by the GDP. Okay, the size of the trade. So if the trade openness increases by 1 percentage points, the growth rate of GDP per capita will increase by 0.14%. Or you can say that if the economy is open for trade, now if it increases by 10 percentage points, then the growth will increase by around 1.5%, right? So, that's a good result, right? If you increase the trade openness by 10%, then if you increase the growth rate by 1.5%, then that's a great achievement. So, in this way, you can interpret. And see, you compare the result. What I have raised here is the result from random effect. There, the coefficient is 0.1. Here, the coefficient is 0.1, and here it is 0.14. So there is a drastic difference. There is a drastic difference, almost 50, 40, 41% difference, right? So if you are not choosing the right
So again, he has lost connect, I think. We are not able to listen.
you go to view fixed random effects, cross-section effects, which will give you the the deviation of individual intercept from the mean. Okay, and you can conclude from these coefficients and say that when your x is increasing by this much or 1 unit, the dependent variable is going to increase by this much unit. So what you need to take care is, when you have a data set, panel data set, you check whether there is one-way effect or two-way effect. Then you choose between pooled, fixed and random effect using the appropriate test. And it all depends upon the data. See, this data set is telling you that this is a fixed effect. Okay. So you are not choosing. This is coming from the data. So you are allow the data to tell you the story rather than you picking up a particular technique. Okay. So with this, I will wind up the session. Thank you. And if you have any queries, we can, take it.
So, one simple question. Sir, here you are showing the equation in E views. In this, C is your cross section data and X is your period data, period coefficients.
No, X is the independent variable.
Okay, and C, so
C
here
is the
you are saying
constant. Yeah, C is the
constant.
constant.
Okay, so the coefficients we have to read it like this because the probability is saying both are significant.
Yeah, yeah.
Is it okay,
Yeah.
sir? Yeah, thank you, sir. I really appreciate the way you have taught us, sir. Because this is first time I'm listening this and I'm trying to learn it. Really, a big thanks to you, sir.
Yeah, thank you. Thank you. So, and if you have any suggestions, that will improve, the way I am delivering. So, if
So,
anyone has any suggestions, please let me.
so my humble request, if you can spare 10 minutes in eView, if somebody can show us the entire analysis, this is the way the data is entered, because I have learned eView long back for Archcash modeling. So there we were.
Excuse me, ma'am. Ma'am, Nirmala ma'am, if
yeah.
you are very particular about e-views, I can show you. Don't worry.
Okay, so the same example, if you can show it, okay, this is the way the analysis is done, and we have to read it like this. It will be really great, great help to all of us.
Yeah, I will
think
show
so.
you, ma'am, how to get the things done. Don't
Sure,
worry.
sure. Yeah. Thank you so much,
Yeah,
sir.
okay.
Yeah. Okay.
Any more questions?
Dr. Ravi, thank you so much for the very interesting session. I have a very basic question regarding the data, because I never use the panel data. The data shows the annual data, but how we are calling it as a panel data it is. Because financial openness is something like we won't get the data, right? Could you please explain how we are calling this data as a panel data? Because when it's showing in yearly data, right?
Let me share it again. Okay. Can you see the data set?
Still not. Okay.
Excel?
Oh, no.
No, sir, not yet.
1 second. I think, I have not shared then.
Yes, yes.
There,
Now we can.
there.
Yes. No, wait.
Can you see it now?
No, still not. Now we can see. Yes, yes.
Okay. Yeah. I think, there is a lag.
I'm asking this question like, I'm working with the same page like a financial openness index, but still not reached to the panel data. So it would be very helpful. Yeah.
No, see, here you can see that, the data starts from 1980. You come down and, for 40th row, you can see it is 2017. So this is for one particular country. Okay. And the data starts for the next country from 41st, row. And you can see that when we come down, we are jumping into the third country. So total we have data from 5 cross sections, 5 countries. Okay.
Yes.
For, the data is from 1980 to 2070. So here in the reviews as well, you can see that, the range of the data. It is from 1980 to 2017 and multiplied by 5. So this indicates that there are 5 cross sections. And let me, this is the way I have defined it. So here you can see that this annual data, but this is from, this is for 5 cross sections from 1980 to 2070. Is it clear? I think, I have answered your question.
Yes. Okay. Regarding this financial openness, the data which you have showed, like, is it estimated? Yeah, it's available.
No, this is not financial openness.
Yeah.
This is this is trade openness.
Right?
Export plus import divided by the GDP. So that is one indicator of trade openness. See, if you are interested in financial openness, there are various indices available. Right, I think not recently, in 2013, Chin and Ito came up with an index. Otherwise, the widely used, financial openness is in the same way we have constructed the trade openness. You can include, the capital inflows plus capital outflows. So divided by the GDP.
Yeah.
So that will tell you about the total flow of finance, between countries.
Okay. Okay. Thank you. Thank you so much.
Any questions? Any more questions? Rafi, actually, we have few questions.
Yeah.
People are asking whether you can spend some time on endogeneity. Before that, they ask whether you can use data or EVS is the best software to estimate panel.
See, for panel data, I would suggest this data because these it all depends upon which methodology you are using. Okay, for if you are going for this whatever we discussed today, the EVS is enough, and EVS is menu driven, so that it is easy to estimate. But say if you are estimating the panel co-integration, you can go for the EVS. I know, but say if you are estimating panel wear model, you cannot go for EViews, which has some limitations. So you have to go, I estimate using Stata. Stata is better. And same way, if you are going for panel ARDL model, you can go for Stata rather than going for EViews. Because in the EViews, see, there are different variants of panel ARDL model. Like you have pooled mean group estimator, and and the the pooled completely pooled model. So there you can estimate only the pooled mean group in EViews. So EViews has limitations, especially in terms of the panel data. It all depends upon which methodology you are using.
Okay. Somebody is asking about unobserved heterogeneity.
Okay, what is the question?
So the question is Sujit Mondal, he is not posting the question properly. Let's wait for him. There are a few more questions regarding in a panel data, what if both intercepts as well as slope coefficients are different for different cross-section units? Is there any specific panel data model to analyze such data? I think you can see the questions in the chat box even. Rafi? I think he lost the connection. Rafi? Dr. Rafi? Okay. Okay, actually, Rafi is not. Rafi, are you available? Yeah, actually, Dr. Sri Lakshmi Narayana, I can answer your question, I think. You are asking about the cutoff points of R square, right? If you're dealing with panel data, I think there is no need to bother much about R square, because the R square is nothing but which explains the coefficient of variation, which will tell you how much variation happens in a dependent variable or a change in independent variable. But here in panel data, we may have a balanced panel or unbalanced panel. The data may have discontinued when there is no any minimum observations required. So in that case, R square does not have much role in explaining the cutoff points. Lakshmi Narayana? I think.
Yes, sir. I'm listening to your answer.
Yeah, Sujit Mondal, I think you asking, could you please explain a little bit on what? I think Rafi? No, I think Rafi, are you available? He lost a connection. Any questions? You just posted once he comment.
Sir, I have a query.
Yes, please.
Sir, it's related to time series. Sir,
Yes,
like
please.
when we go for the primary survey in cross-sectional, we have this methods to estimate the sample size, right? We this variant of this method of variable into n number of. I mean, there are methods to find out what should be an appropriate sample size. Is there any way in time series to make sure that this particular time period is enough for the estimation of the results? Like what number of years should be sufficient?
Yes, please. Rafi, just a minute. They're asking some
Yeah.
other question in time series. I will answer, then you can.
Please.
Somebody is
go.
asking about a few more questions. I answered, but anyhow, you can check it out in the chat box. Okay.
Yeah.
Rahul, I think is it
Go
Rahul
ahead.
the question, right?
Go ahead.
Rahul?
Yes, sir.
Yeah, actually, the point is in the cross sectionals, we are using certain methodologies to choose number of sample size and all. But in time series, there is no any fixed rule for that. Generally, what we people do is we try to pick a data points which satisfy the condition of normality. There is no any rule of thumb. Even you can't find anything in the textbooks, but the rule of thumb is if your sample size is more than 30, that sample will satisfy the condition of normality. Okay, we have a bell-shaped curve, right? Yeah, it is believed that if the sample size is more than 30, then you have a normally distributed thing. So if that condition is satisfied, most probably you can go for any time series analysis. Minimum 30 observations. There is no any rule of thumb. That's what I'm saying. Okay. But if you want to apply certain models like high integrated model like a war model and impulse response or something like that, it needs some huge database. Huge data numbers is required. Then only you can get the better results. For a minimal number of observations, it won't give you the better results.
Actually,
yes, Rahul.
I am new to this time series analysis. I have done work on cross sectional. Actually, I am thinking of to present a paper on this GSDP of particular about forecasting the GSDP of particular state, and the data is available from 2003 to up to 19. So is this data sufficient for?
Actually, that's what I'm saying. If that is the only data is available, but I can say it is not a good data. It's not good enough to be a forecasting. But if you have more data points, you may have better forecasting. That is what my suggestion is all about. But as far as GSDP is concerned, if I'm right, almost GSDP is available from all the states from the year 1950s itself.
No, sir. I'm talking about these Uttarakhand, Chhattisgarh, and Jharkhand.
Yes.
The data.
So that okay. What you have to do is there are certain methodologies are available to decompose the data. Before 2013, both states are is joined with Uttarakhand is with Bihar, right? If I'm right.
No, Uttar Pradesh, sir.
UP, right? So if you there are certain methods to decompose the GSTP, but that's a little technical. So if that is the only data available, you don't have any choice. You can go with that forecasting. Doesn't nothing wrong in that.
One last query. Sir, can I connect to you after this FDP so that you can?
Yes, please. Anytime. No issues.
So can I get your mail or something?
Yeah, sure. We have 2 more days. Don't worry. I'm not going to run away on today itself.
Okay, sir. Thank you, sir.
Yeah, sure, Rahul. Rafi, you can go with that, man.
Yeah. As you know, shall I add something to his question?
Yes, please.
Maybe if you can get quarterly data, say you have from 2003, right? If you can get quarterly from 2003 for this particular state, then I think that will be more than sufficient.
Yeah, it's a valid suggestion. Quarterly data, you can think about it.
And I know, see, who is interested in the annual GDP, right? Rather, we always look at quarterly GDP. So my suggestion would be you see whether quarterly GDP is available. Then you can forecast. Say if you are able to forecast for next 4 quarters, I know that will be a good study.
Okay, sir.
Yeah, Rahul, actually, one more thing. You can get the data from EPW. EPW used to publish a source on EPW and Research Foundation. Okay, they used to publish a EPW data series from 1951 for all the states. So if you have an access over that, you can get, as mentioned by Dr. Rafi, correctly, you can go for quarterly data. Some 10 years means you can get 40 observations. Obviously, that normality condition will be satisfied. You can go for any model. Suppose you are getting some bad results, that may be because of less data points. So to avoid that end only, I'm suggesting to think about 30 observations. There is no any rule of thumb. Make it very clear. There is no any such rule. But in statistics, it is believed that if the sample size is more than 30, your distribution satisfied the condition of normality. But that question itself, that condition itself is questionable, because what happens if it is 29? Why not it satisfy the condition of normality? That is a separate debate. I'm not going to that. But as of now, it's a general belief that you can pick a data which satisfy the condition of normality. When the data will satisfy the condition of normality, more than 30 observations. So to avoid the other things, you can think about some 30 observations for your estimation. As mentioned by Dr. Rafi, yes, quarterly data is the best choice.
Okay, sir. Thank you, sir.
Yes, thank you, Rahul. Rafi, there are a few more questions, man. Somebody is asking about heterogeneity and endogeneity.
What is the question?
You can see the chat box also, man. Yes. Sujit Mondal posts some question. Could you please explain a little bit on unobserved heterogeneity and its relation with endogeneity and exogeneity?
See, the first question, unobserved heterogeneity means, see, you can see different behavior for different individuals. Say, when you are studying about the relationship between two variables, different individuals behave in different way. Now, this would be because of different reasons, which are unobservable. Say, you consider the efficiency of an individual in work. That might be because of different, some inherent reasons or some reasons which you cannot observe from the data. Okay, so that's what I mean by unobservable, or unobserved heterogeneity. So this is the reason for the heterogeneous behavior of different individual units. I think I have answered the question on unobserved heterogeneity. But can you explain what do you mean by the second question? You want me to explain about the unobserved heterogeneity and the relation between endogeneity and exogeneity. See, the concept of endogeneity is different, or the concept of exogeneity is different. See, that is not related with the heterogeneity which we are talking about. See, when say if you have uh, in OLS, we assume that the independent variable is not correlated with the error type. So that is, that is, we are assuming the exogeneity. Okay. Now, say if you take a simultaneous equation model, say if you have consumption on the left-hand side and income on the right-hand side, let's say consumption function. Now, if you take the identity, y is equal to c plus I. Okay, so in the first equation, you have y on the right hand side, I mean as a independent variable, and in this second you have y as a dependent variable. Similarly, c is the dependent variable in first equation and independent in the second equation. I mean the national income identity. So in this case, what happens is that there is a bidirectional causality, which we call it as endogeneity. Okay, so and there are different methods available to deal with the endogeneity. Like you can go for the GMM or the WARE model. So there are different methods, or the indirect least square or 2SLS is that's widely used method. So I hope you are talking about this endogeneity, right? So the endogeneity is a different concept, or the exogeneity is a different concept, but the heterogeneity I'm discussing about is the difference between two cross-section units.
Yeah, any questions? Yeah, there are a few more questions, Rafi. Maybe a final question. People are asking, I already answered them, but still you can answer them. They ask whether there is any minimum cutoff for R square in panel data.
See, nowadays, R square, who is looking for, right? The R square is not, R square, especially in panel data, we do not look for. Therefore, you do not have a particular cutoff. But R square you can use for comparing two models. Say, if you have one model with, say, 3 independent variables and, another model with some, where the dependent variable is same. Then you can compare using the R square and say that this model explained the variation in the dependent variable more than the other model. Otherwise, there is no cutoff as such. Higher R square means better, but again, Nowadays, if you read the papers, you cannot say somebody, you cannot see somebody talking about the R square there.
Yes. Any questions? Any more questions? Participants? Yeah, half of them don't left. Yes.
Sir, good evening, sir.
Yeah.
My question is, you spoke about that one-way and two-way effect, no, sir, in this panel.
Yeah.
It was new to me. I just have an idea. A question which I had in my mind is, will this have an effect or impact on our result if we avoid this? Or should we get into, like, we should be so cautious about it to check for one-way and two-way and then get into the analysis, sir?
See, usually the period effect, this two-way effect is not very common. Because each year something happening and which is affecting all the cross-section unit is not a very common thing, you can see. So even if we are ignoring the two-way effect, usually it will not have much effect. Among the cross-section units. So if you ignore the one-way effect, I mean the fixed effect, then if you are going for the pooled model, then that can have a larger impact. But still, it is better you check for both.
Okay, sir. Okay, thank you, sir. Thank you so much, sir.
Yeah,
Okay, maybe final question. There is one more question. Just with that, we can close.
Yeah. I can see one question in the chat box.
Yes, please.
A panel data model when slope coefficient, any panel data model when slope coefficients of cross-section units are also different. If you are considering the different intercept and different slope coefficients, then which is equivalent to do the time series analysis for all the cross sections separately, right? Both are same. So with respect to the ordinary least square, or what is equivalent to the ordinary least squares, you do not have a model which explain both the slope, which explain the difference in slope as well as the intercept. There is no model as such which is equivalent to the ordinary least square method. But whereas say when you talk about the you consider the panel ARDL model, where you can see that there is in the ARDL you consider both the short term and long term effect, plus you have an intercept, right? So there you can see that there is the mean group model which allows for the intercept, the long term parameter as well as the short term parameter to vary, okay, across cross section units. And you have a pooled mean group model which allows only, if I remember well, which allows only the short term or long, I don't remember exactly, which allows only either the long term or short term parameter to vary. So there it is available. But in case of the usual, what is equivalent to the ordinary least square method, you do not have a model to, which allows you to vary both. But if you are interested in that, you go for, that separate time series models of these cross-section units.
Yeah, I think we can close already. He took some half an hour extra. Induja, before that, I thank personally Rafi for accepting our invitation. Actually, I also want to make a personal thanks because we are shifting your session, preponing your session. Thanks for your kindness in accepting all the pains. Yeah.
Thank you. I should thank you and your department for giving me this opportunity, to interact, and it was really an interesting session. Thank you.
Induja.
I would like to thank our speaker today, Dr. Rafi sir, for this extraordinarily thought-provoking session. This session was no doubt beneficial for the participants as researchers from mixed disciplines. The practical session was also has also helped us widen our scope in the subject. Thank you, sir, for taking time out from your busy schedule to be present here today.
Yeah, for participants, Rafi, I will call you Rafi. Thank you, Dr. Rafi.
Yeah, thank you so much.
Yeah, for participants, tomorrow morning we have a session on interesting session on volatility models. Those who are from financial background who is very particular, please join on time. Okay. So if you miss something in the very beginning itself, it's very difficult to follow. So it's for those who was very serious. Almost 1/3 of the participants left the meeting. So those who are available here, just make sure that you attend on time. Okay.
Yes, sir. Thank you, sir.
Yeah.
Thank you, sir.
Thank you all.
Thank you, sir.
Thank you.